Nothing in the universe is supposed to be faster than light. It is the rule that shapes our reality and locks humanity into a tiny corner of space. And yet, we can't help but wonder, what if that barrier could be broken? What would it mean for time, for distance, for the future of civilizations like ours? For over a century, scientists and dreamers have searched for cracks in the rulebook of the cosmos. Strange particles, warped space, shortcuts through wormholes, all of them hint at ways to outrun the fastest thing in existence. If we ever succeed, the consequences would be greater than anything else humanity has ever imagined. This is the story of what could happen when we finally break the speed of light. Why the speed of light is the ultimate cosmic limit. The speed of light is one of those numbers in physics that seems simple when you first hear it, but the more you think about it, the stranger it becomes. Light moves at about 300,000 kilometers per second in empty space. That means it can circle the Earth more than 7 times in just 1 second. At first, this might sound like just another fact about nature, like how fast sound moves through air or how water boils at a certain temperature. But the speed of light is not just another speed. It is a boundary built into the very fabric of the universe. It is the fastest possible motion, the ultimate cosmic speed limit. No object, no signal, and no piece of information can move faster than it. To understand why this is the case, we need to turn to Einstein's theory of relativity. Before Einstein, many scientists thought that motion was relative in a simple way. If you throw a ball forward while riding on a moving train, someone standing on the ground would see the ball's speed as the train's speed plus the ball's speed. That made sense for normal objects and everyday motion. People assumed that light would behave the same way. If you turned on a flashlight on a fast-moving train, the beam of light should look faster to someone standing on the ground. But experiments showed this wasn't true. Light always moved at the same speed, no matter who was watching it or how fast they were moving themselves. This was one of the great shocks of physics. It forced Einstein to rethink space and time themselves. Instead of light adjusting its speed to match the observer, space and time bent and shifted so that light's speed stayed constant. In his theory of special relativity, the speed of light became the unchanging rule of the universe. Everything else, distance, time, and even mass, had to give way to this rule. The most famous part of this theory is that the faster something moves, the more its mass appears to increase. This doesn't mean you suddenly gain extra atoms as you run faster. Instead, it means that in terms of energy and resistance to motion, your mass effectively grows. At low speeds, this increase is so small that we don't notice it. But as you approach the speed of light, the effect becomes extreme. To push something faster, you need to give it more energy. At everyday speeds, this is no problem. But near the speed of light, the energy required grows enormously. The math shows that as you get closer and closer to light speed, the energy you need becomes greater than anything you can imagine. At exactly the speed of light, the energy needed would be infinite. That means you would need an endless supply of fuel, something the universe cannot provide. At that point, your effective mass would also become infinite, and nothing can push something of infinite mass any faster. This is why no object with mass can ever reach light speed. The barrier is not a matter of technology or effort. It is a law written into the structure of reality. This idea might sound abstract, but it has direct consequences for how the universe works. If faster than light travel were possible, cause and effect would break down. Events could happen in reversed order, depending on the observer. Signals could be sent back in time. The very idea of time and order would collapse. By making the speed of light a hard limit, the universe protects the chain of cause and effect. It ensures that time has a direction and that events cannot undo themselves. It also means that the universe has a built-in horizon. No matter how hard we try, there are regions of the cosmos we will never reach. A galaxy billions of light years away sends out light, but if that light takes billions of years to arrive, it sets the pace of discovery. We cannot skip ahead. Even if we could build the fastest rocket imaginable, It could only approach but never match the pace of light. Our universe is vast, not just in size, but in the way it limits motion itself. Some may wonder about the particles of light themselves, called photons. They have no mass, and that is why they can move at the speed of light. But even they cannot exceed it. They exist in a strange state, always moving at exactly that speed, never slower and never faster. If they tried to go faster, the math of relativity would break down. They would no longer fit within the rules of space and time. The same goes for other massless particles, such as the gluons and possibly the elusive gravitons. For them, moving at the speed of light is not just an option. It is the only way they can exist. This cosmic speed limit also explains why the idea of infinite speed is impossible. Imagine if you could jump instantly from one point to another, crossing light years in a blink. That would mean skipping across space without moving through time. Relativity shows that space and time are tied together as one structure, called space-time. To move faster than light would be to tear through that structure in ways it cannot allow. The universe is held together by these rules, and breaking them would mean breaking the order of reality itself. There have been many ideas in fiction about faster-than-light travel. They are exciting to think about, and scientists have even studied whether some of them could fit within the rules of physics. But at their core, they rely on bending space itself, rather than breaking the speed of light. Even in these speculative ideas, the speed of light remains the fundamental rule. In this sense, the speed of light is more than just a number. It is a foundation. It ties together energy, mass, space, and time. It sets the boundaries of what can happen and when it can happen. Without it, the universe would have no clear rules, and events might not unfold in any stable way. What looks at first like a limit is also a form of protection. It creates order in the chaos of the cosmos. When we look at the stars, we are looking into the past because of this rule. The light from a distant galaxy has been traveling for millions or even billions of years before reaching us. The speed of light fixes how far back in time we can see, and it links the act of observing with the passage of time. Every glimpse into the night sky is a direct result of this cosmic speed limit. The energy wall. Why infinite power is demanded at light speed. The energy of an object is linked to both its mass and its speed. When you move slowly, the difference between everyday physics and relativity is too small to notice. But as you accelerate, relativity begins to dominate. The energy you need to push a spacecraft from 10,000 kilometers per hour to 20,000 kilometers per hour is large but possible. The energy to push it from 100,000 to 200,000 is far greater, but still something we could imagine if technology allowed it. Yet if you try to push that same craft from 99% of light speed to 99.9%, the energy demand skyrockets. Each fraction of a percent closer requires more energy than all the steps before it. Physicists compare this to climbing a mountain that becomes endlessly taller as you climb. No matter how much progress you make, the summit pulls away. Each step costs more effort, and eventually, no amount of fuel or power will be enough. We can see this energy wall at work in particle accelerators. These machines, such as the Large Hadron Collider in Europe or the Tevatron that once ran in the United States, are built to slam particles together at tremendous speeds. Protons inside the collider are pushed by magnetic fields, making them circle faster and faster until they reach speeds close to light. The engineers feed more and more energy into the system, yet the particles never break past light speed. Instead, their mass, measured in terms of energy, keeps growing. They become heavier in a sense, harder to push, even though they are still just tiny protons. At the LHC, protons can reach 99.999999% of light speed, but no matter how much energy is added, that last fraction of a percent cannot be reached. This is one of the best experimental proofs of relativity's rules. It shows us that the barrier is not just a theory on paper. We have built machines that tried to push against it, and the wall held firm. Even the most advanced accelerators humanity has ever created cannot cheat it. Instead, they confirm it with every experiment. This also explains why we cannot simply imagine building a rocket with a bigger engine or a new type of fuel to push past the barrier. This energy wall shapes the future of space travel. Even if we imagine technologies far beyond today's rockets, fusion drives, antimatter engines, or concepts we have not yet invented, the same rule will apply. These engines might carry us much faster than we can travel today, perhaps to a significant fraction of light speed. They might let us cross the space between stars in decades rather than thousands of years. But they will still meet the same wall. The energy demand will grow, and light speed will remain out of reach. The strange thing about this wall is how invisible it is to our everyday lives. A person running across a field or a plane flying through the sky does not notice any unusual change in energy demand. The laws of relativity are present but buried under small numbers. They reveal themselves only when speeds approach the cosmic limit. This is why it took experiments with light and later with high-energy particles to uncover the rule. Human senses alone could never have guessed that such a barrier exists. Another way to picture this is through Einstein's famous equation E equals mc squared. It tells us that mass and energy are two forms of the same thing. As you push an object faster, you are pouring energy into it, and in a sense, that energy adds to its mass. The faster it moves, the more massive it becomes, in terms of the effort needed to push it further. At the speed of light, the mass would become infinite, and so would the energy required. The moment you introduce mass, no matter how small, the rules change. Electrons, protons, atoms, spacecraft, all of them are tied to the wall. The barrier applies equally to the smallest particle and the largest galaxy. Momentum is the measure of how hard it is to stop something in motion. A truck rolling down the road at high speed has much more momentum than a bicycle going at the same speed. That is why the truck takes longer to stop and why it hits with greater force. In everyday life, momentum is straightforward. But in Einstein's theory, momentum grows much faster than in the old Newtonian view. If you try to push the math further, asking what happens if you go faster than light, something even stranger appears. The equations no longer give real numbers. They produce what mathematicians call imaginary values. In normal physics, mass and momentum are always real and measurable. You can weigh a rock. You can calculate the momentum of a baseball, and the numbers make sense. But in the equations for faster than light speeds, mass and momentum stop being real quantities. They slip into values that do not exist in physical reality. A momentum that is imaginary cannot be measured, cannot be observed, and cannot interact with the rest of the universe. It is like trying to calculate the weight of a shadow or the volume of a dream. When you calculate momentum at speeds below light, everything works cleanly. At the exact speed of light, the momentum shoots toward infinity. Beyond that, the equations step into impossible territory. This is why scientists sometimes describe light speed as a boundary line on a map of physics. Some scientists have speculated about what might exist in that blank space. The idea of tachyons, hypothetical particles that always move faster than light, came out of these strange equations. According to the math, if such particles existed, they would never slow down below light speed, just as ordinary matter can never speed up to it. But tachyons have never been observed, and many physicists think they cannot exist at all. Their properties would be so bizarre that they would break the stability of the universe. Why expansion of space outspeeds light without breaking physics? Light cannot be outrun by rockets or particles, yet entire regions of the cosmos are slipping out of sight, carried beyond reach at superluminal speed. At first, this seems like a contradiction, but the explanation lies in a subtle difference. The galaxies themselves are not moving through space faster than light. Instead, space itself is stretching, and that stretching has no speed limit. To see how this works, imagine dots on the surface of a balloon. If you inflate the balloon, the dots move apart, not because they are crawling across the surface, but because the surface itself is expanding. Each dot stays still on the balloon, but the distance between them grows. The same thing happens with galaxies in the universe. They are not flying through space at impossible speeds. Instead, the very fabric of space is expanding, carrying them farther apart as time goes on. This expansion was first discovered by Edwin Hubble in the 1920s. He observed that galaxies beyond the Milky Way showed a redshift in their light, a stretching of wavelengths that meant they were moving away. The farther a galaxy was, the greater the redshift. This led to the understanding that the universe is not static, but growing. Later, the Big Bang theory was built upon this discovery, describing a universe that began in a hot, dense state and has been expanding ever since. As the universe expands, there is no maximum rate at which space itself can stretch. Over small distances, the effect is tiny, barely noticeable. But over billions of light years, the stretching accumulates. A galaxy that is very far away can be carried away from us faster than the speed of light. The expansion of space stretches the distance faster than light can cross it. It is as though the finish line is running away quicker than the runner can sprint, no matter how fast the runner tries. Cosmic inflation, the rapid expansion thought to have taken place just after the Big Bang, magnifies this effect even more. In a fraction of a second, space itself ballooned at a rate that dwarfs the speed of light. Entire regions of the infant universe were stretched so far apart that they became permanently disconnected. This process explains why the universe looks uniform on large scales and why we see the cosmic microwave background spread so evenly. Inflation is the ultimate example of space expansion outpacing light, yet it still does not break the rules of relativity. The galaxies were not zipping through space faster than light. Space itself was stretching, and relativity allows that without contradiction. This difference between objects moving in space and space itself expanding is one of the most important clarifications in modern cosmology. If you could somehow freeze the expansion and measure the speed of a galaxy relative to its local surroundings, it would still be moving at normal speeds, well below light. But when you step back and measure the growing distance across billions of light years, the expansion makes it appear as though the galaxy is retreating faster than light. The implications of this are profound. They mean that our observable universe, the part we can see and study, is only a fraction of the whole. Beyond the horizon lies an unknown expanse, perhaps filled with galaxies, stars, and even planets, but forever beyond contact. These regions are as real as our own, but to us, they are ghosts that will never be visible. Expansion ensures that their light can never bridge the gap. This also helps explain why the night sky is not infinitely bright, even though the universe contains countless stars. If the cosmos were static and eternal, every direction would eventually show the surface of a star. But because of expansion and horizons, much of the universe remains hidden and the sky is dark. The rule of light speed, combined with the stretching of space, sets the boundary of what we can know. Measurements of the cosmic microwave background, surveys of galaxies, and observations of distant supernovae all show that the expansion of the universe is real and even accelerating. Dark energy, the mysterious force behind this acceleration, makes the horizon shrink faster, pushing more galaxies beyond reach with every passing moment. Each year, more of the universe slips away. On the one hand, no particle and no signal can outrun light. On the other, the universe itself casually stretches faster than light without breaking a single law. It is as if nature is telling us that the rules apply within space, but space itself plays by different rules. This creates a strange balance. Motion is limited, but expansion is free. When we think about the future of the cosmos, this rule carries sobering consequences. Billions of years from now, more and more galaxies will slip beyond the horizon. Eventually, distant galaxies will disappear from view, leaving only the nearest cluster of galaxies visible. The larger universe will still exist, but its light will never reach us. Future observers may look at the sky and believe the cosmos is empty beyond their local neighborhood. Expansion will hide the truth from them, just as it already hides countless galaxies from us today. This strange duality, that nothing can move faster than light, yet the universe itself can grow faster than light, remains one of the most fascinating aspects of modern cosmology. It shows us that the laws of physics are not broken by expansion, but redefined by it. The cosmic speed limit is real and absolute for travelers within space, but space itself follows its own logic. The temptation of tachyons, imaginary particles that shouldn't exist. The name tachyon comes from the Greek word for swift. The concept first appeared not because scientists went looking for faster-than-light particles, but because mathematics seemed to suggest them. When physicists explored the equations of relativity and quantum theory, they found that certain solutions hinted at particles with imaginary mass. This does not mean mass that exists in the imagination. It refers to numbers in mathematics called imaginary numbers, which involve the square root of negative values. These solutions looked nonsensical, but they could also be interpreted as particles that are real, with the strange property of being unable to go slower than light. Out of this idea, tachyons were born. At first, the thought was intriguing. If tachyons existed, they might open doors to whole new forms of physics. They could potentially transmit information across vast distances instantly, bypassing the limits of space and time. They might allow communication across the universe without waiting millions or billions of years for light signals to travel. In some speculative visions, they could be used to send messages backward in time. These possibilities made tachyons tempting, almost like forbidden fruit in the scientific garden. The problem is that tachyons also create contradictions. Imagine writing a message today, only for the recipient to read it yesterday. That would mean the effect comes before the cause and the arrow of time. The one-way flow from past to future collapses. Physics relies on causality, the rule that causes lead to effects in a consistent order. Tachyons, if they were real, would threaten this foundation. The universe might no longer make sense. Events could loop back on themselves, creating paradoxes where actions undo their own existence. Because of these contradictions, many physicists treat tachyons more as a mathematical curiosity than as real particles. They appear in equations, yes, but equations can often produce solutions that do not correspond to physical reality. For example, in early versions of quantum field theory, tachyon-like terms showed up in the math. Instead of proving that such particles exist, physicists later realized that these terms pointed to instabilities in the theory, a sign that the system needed to be redefined. Once corrected, the tachyons vanished. It was as if the equations were warning, something is wrong with your model. The supposed particle was more like a ghost, a signal of error, rather than a real inhabitant of the universe. Still, the allure of tachyons has not gone away. They continue to appear in speculative theories, particularly in attempts to unify different parts of physics. In string theory, for example, tachyon-like states emerged in some versions of the equations. Rather than being real faster-than-light particles, these tachyons again pointed to instability, suggesting that the strings themselves wanted to rearrange into a more stable form. Some scientists interpret this as a process similar to a ball rolling down a hill into a valley, a transition from one state of reality to another. Tachyons in this sense are not literal but symbolic. Beyond theory, no evidence of tachyons has ever been found in experiments. Physicists have searched in particle accelerators, where high-energy collisions might reveal exotic particles, but no faster-than-light signals have ever appeared. Cosmic ray observations, which catch particles flying through space with energies far beyond what we can create on Earth, have also shown no signs of tachyons. Even in areas where anomalies once raised eyebrows, such as early measurements of neutrinos that seem to move faster than light, later analysis revealed experimental errors. The universe, it seems, has yet to offer any proof that tachyons are real. And yet, the idea lingers. History is full of cases where something once thought impossible later became real. The notion of atoms, black holes, or quantum tunneling all began as strange, even absurd ideas before experiments confirmed them. Tachyons, though still unsupported, occupy a space in the imagination where the boundaries of physics blur. They force scientists to ask if the rules we know are truly unbreakable, or are they just the limits of our current understanding? Writers have used tachyons as the basis for faster-than-light drives, instant communication systems, or time travel devices. In these stories, tachyons often play the role of the magic ingredient that allows humans to escape the chains of light speed and explore the galaxy freely. They symbolize the dream of breaking out of our cosmic prison, of stepping beyond the horizon that the speed of light enforces. Even if physics rejects them, imagination clings to them. If tachyons did exist, they might show that time itself is not as rigid as we think. Our sense of past, present, and future could be just a local illusion, a construct that breaks down under more extreme conditions. The contradictions they create, messages arriving before they are sent, causes following effects, might not mean the universe is broken, but that our logic is too limited. Perhaps in a reality larger than ours, these paradoxes would find a resolution. Perhaps what seems impossible in one framework could be natural in another. Quantum tunneling and the illusion of superluminal escape. Quantum tunneling is one of those strange ideas in physics that feels like it should not be real, yet experiments prove it again and again. In the everyday world, if you throw a ball at a wall, the ball either bounces back or smashes through, depending on how strong the wall is and how fast the ball is moving. There is no third option. But in the world of quantum mechanics, particles do not always follow such clear rules. Sometimes, when faced with a barrier, they do not have enough energy to cross. They simply vanish on one side and reappear on the other. This is tunneling, a ghost-like passage through obstacles that should be impenetrable. At first glance, tunneling seems to break the cosmic speed limit. The process looks instantaneous, as though the particle has jumped across space faster than light could travel the same distance. Some early measurements of tunneling time seem to show just that. Electrons or photons appearing on the far side of a barrier quicker than the laws of relativity should allow. Headlines occasionally seized on these results, fueling speculation that nature might be hiding a secret backdoor to faster-than-light motion. Could this be the loophole that lets us escape Einstein's chains? The deeper the effect was studied, however, the more the illusion unraveled. To understand why, it helps to look closely at what tunneling really means. Particles in quantum mechanics are not tiny billiard balls moving along neat paths. They are better described by waves of probability, ripples that spread out through space. When such a wave encounters a barrier, part of it reflects back, but part of it also seeps into the barrier itself. If the barrier is thin enough, the probability wave does not vanish completely but leaks through to the other side. This is why tunneling is possible, not because the particle smashed through, but because its presence was never limited to one side in the first place. The strange part comes when we measure the time it takes for this to happen. If you track a single particle, you cannot watch it travel through the barrier step by step. All you can measure is whether it appears on the far side or not. In some experiments, the particle seems to show up faster than light could have crossed the same gap. But this does not mean the particle actually outran light. Instead, it reflects how the probability wave interacts with the barrier. The apparent speed is a byproduct of how the wave reshapes itself, not the movement of a real signal carrying information. This distinction is crucial. Physics draws a hard line between the movement of probabilities and the transfer of usable information. While tunneling can create the appearance of instant passage, no actual message or cause and effect link can cross faster than light. If you try to use tunneling as a way to send information at superluminal speeds, the effort fails. The random nature of quantum outcomes prevents you from controlling what happens. You cannot decide when a particle will tunnel or force it to appear on the other side exactly when you want it to. All you can do is measure the odds after the fact. Without control, there is no message, no communication, and no true violation of relativity. One way scientists confirmed this was by carefully analyzing tunneling with light itself. In laboratory setups, pulses of photons were sent through barriers designed to mimic obstacles. Some parts of the pulse seemed to emerge earlier than expected, almost as if light had skipped ahead. Yet when researchers checked whether any usable signal had outrun the rest, the answer was always no. The shape of the pulse had changed, but the limit set by the speed of light remained firm. The illusion came from the way the front edge of the wave was reshaped, not from any real leap beyond Einstein's boundary. Quantum tunneling is a vital part of how the universe works. Without it, stars would not shine. In the cores of stars like our Sun, nuclear fusion depends on tunneling. Protons, the positively charged particles at the heart of atoms, naturally repel one another. They need enormous energy to overcome this repulsion and fuse together, releasing light and heat. At the temperatures found in stars, the protons should not have quite enough energy to fuse as often as they do. Tunneling provides the extra push. It allows them to slip through the energy barrier and combine, fueling the stars that light our sky. This everyday role in cosmic life shows how tunneling, while strange, is deeply woven into nature. It is not a bug in the system, but a feature that makes existence as we know it possible. And yet, for all its oddity, it does not grant the gift of faster-than-light travel. It bends our sense of what motion means, but it does not bend the ultimate rule set by relativity. The barrier remains, even if the pathways around it sometimes trick the eye. What tunneling does reveal is how slippery the idea of speed becomes when we leave the classical world behind. In our daily lives, speed is simple, but at the quantum level, where particles spread out as waves and exist as clouds of probability, speed loses its clear meaning. Tunneling highlights this by producing effects that look faster than light when measured one way, yet hold to Einstein's limit when measured in terms of information and cause. Some scientists continue to explore tunneling times, searching for ever sharper ways to measure the process. Their experiments use ultra-fast lasers, capable of probing electrons with attosecond precision, an attosecond being a billionth of a second. Even with this extreme resolution, the results continue to support the view that tunneling does not carry signals beyond the speed of light. The mystery lies not in breaking the cosmic speed limit, but in understanding how probability and time weave together at scales where our everyday notions no longer apply. Entanglement's trick. Why spooky action at a distance isn't travel. Quantum entanglement reveals that two particles, once linked together, can continue to share a connection even when separated by enormous distances. Change something about one particle and the other seems to respond instantly, no matter how far apart they are. To Albert Einstein, who was one of the first to think deeply about this, the effect seemed so strange that he called it spooky action at a distance. For him, it looked like nature was allowing information to travel faster than light, something his own theory of relativity said should be impossible. The heart of entanglement lies in how quantum particles behave when they are created together. Imagine two electrons born from the same event. Their properties, like their spin, which can be thought of as a tiny internal compass, are linked from the start. When the particles fly apart, the rules of quantum mechanics say that their spins remain connected. If one is later measured and found to be up, the other will instantly be found to be down. The outcome is not determined in advance, but only when the measurement happens. The spooky part is that the second particle seems to know immediately what happened to the first, even if they are separated by light years. At first glance, this looks like a perfect way to break the speed of light barrier. If you can change something about one particle and instantly affect the other, why not use that as a cosmic telegraph? Imagine preparing a pair of entangled particles, keeping one on Earth and sending the other to a spacecraft heading to another star. Couldn't we then use the particles to send instant messages, bypassing the years or centuries it would take for light signals to get there? The problem is that the effect, though real, cannot be controlled in a way that transmits usable information. This is where entanglement tricks us. When you measure your particle, You cannot choose what result you will get. It is random, sometimes spin up, sometimes spin down. The particle on the other end will always show the opposite, but that does not help if you are trying to send a message. You cannot decide in advance that you want to send a yes by forcing your particle to be spin up or a no by forcing it to be spin down. All you get is a random outcome. The instant link is there, but it carries no information that you can control. This is why entanglement, despite appearances, does not break Einstein's limit. It does not allow anything meaningful to outrun light. The spooky action is real, but it is more like a mirror than a message. The instant coordination between particles is a reflection of how they were linked from the start, not a channel through which signals can be sent. The universe, in a sense, set up the answer in advance. The mystery lies not in faster-than-light communication, but in how nature maintains this invisible bond across space. Physicists have set up experiments with entangled particles, separated by kilometers, then by hundreds of kilometers, even by satellites in orbit. In every case, the results confirm that entanglement works at any distance. No matter how far the particles are pulled apart, the link remains. And in every case, no signal has ever been found traveling faster than light. The statistics of the measurements obey the rules of quantum theory, but they never provide a way to send controlled messages across the gap. Some scientists have used entanglement to test the very foundations of physics. These experiments are called Bell tests, named after physicist John Bell, who developed a way to check whether entanglement could be explained by hidden rules we simply did not know about. If the particles secretly carried instructions from the start, the spooky action might just be a trick. But Bell's inequality, as it is known, gave a clear prediction. If entanglement is real, the results would break the limits set by any hidden local rules. And that is exactly what experiments showed. The particles really do share a connection that goes beyond classical physics. Einstein's discomfort was justified. Entanglement is indeed strange, but it still does not open the door to faster-than-light messaging. Instead, what entanglement gives us is something else entirely, a resource for building new forms of technology. While it cannot carry information faster than light, it can be used in quantum computing, where entangled particles act together to process information in ways classical computers never could. It also underpins quantum encryption, where entanglement can be used to create keys that are unbreakable by any eavesdropper. In these applications, the spooky action at a distance is not a loophole to travel faster than light, but a tool for reshaping how we handle information in a secure and powerful way. The persistence of the illusion is understandable. Entanglement looks like a shortcut, a hidden path through the universe's speed limit. But the more closely we study it, the more carefully the universe guards its rule. Even in this most exotic of phenomena, information still obeys the light speed boundary. What moves instantly is not a signal but a correlation, a reflection of the deep unity that quantum mechanics describes. This makes entanglement one of the most beautiful paradoxes of modern science. It shows us a universe that is more connected than we ever imagined, yet still bound by the speed of light. It offers power in the form of new technology, yet denies us the fantasy of instant travel or communication. It keeps the dream alive in our minds, even as it reminds us of the barriers we cannot cross. The Alcubierre drive, warping space instead of racing through it. The Alcubierre drive is one of those ideas that sounds like it belongs only in films, yet it was born from real physics. In 1994, physicist Miguel Alcubierre asked a simple but radical question. What if instead of trying to push a ship faster than light, you changed the space around it? The proposal he came up with suggested that by contracting space in front of a spacecraft and expanding it behind, you could make the ship appear to travel faster than light without ever locally breaking the speed limit. The craft itself would not move through space in the usual sense. Instead, it would ride inside a bubble of warped space, carried along like a leaf on a flowing river. From the outside, this would look like faster-than-light motion. To a distant observer, the ship would cover vast distances in far less time than a beam of light would. Yet inside the bubble, the ship and its passengers would feel no motion at all. They would simply sit within their local patch of space, unaffected by acceleration or drag, as the bubble itself did the work. In theory, this neatly sidesteps the Great Barrier of Relativity. Since nothing inside the bubble moves faster than light relative to its immediate surroundings, Einstein's rules are not technically broken. The idea is elegant, but it comes with enormous challenges. The first and most daunting is the kind of energy required to make such a bubble. To bend space in the way Alcubierre's equations describe, you would need negative energy density, something unlike any ordinary fuel or power source we know. Normal matter, whether it is coal, oil, nuclear fuel, or even stars themselves, all have positive energy. Negative energy, however, is not something we can store in a tank or generate on demand. It shows up only in tiny effects predicted by quantum theory, such as the Casimir effect, where the vacuum between two closely placed metal plates behaves in unusual ways. The amounts involved are minuscule, nowhere near enough to drive a starship. Calculations suggest that to make a warp bubble big enough to carry even a small spacecraft, you might need as much negative energy as the total mass energy of the entire universe. Later refinements have reduced that estimate, but the numbers are still staggering. Even the most optimistic versions demand exotic forms of matter that may not exist in usable amounts. Without them, the Alcubierre drive remains a mathematical dream rather than an engineering project. Even if you could somehow create the bubble, keeping it under control might be nearly impossible. The boundaries of the warp would need to be finely balanced, with space contracting ahead and expanding behind in perfect harmony. Any imbalance could cause the bubble to collapse, trapping or destroying whatever is inside. There are also questions about what happens to radiation and particles caught at the edge of the bubble. Some models suggest they could build up into deadly bursts of energy, released when the bubble shuts down. This raises the unsettling possibility that a warp drive ship arriving at its destination might unleash a destructive blast. Once the bubble forms, signals from inside cannot reach outside in the usual way, because the boundary of the warp itself blocks communication. This means you might not be able to control where the bubble goes or when it stops. In a sense, you would be a passenger inside a runaway pocket of space, carried along without the ability to influence your course. Some theorists have tried to solve this with clever adjustments to the equations, but no clear solution has emerged. Despite these obstacles, the Alcubierre drive continues to attract attention because it represents something rare, a theoretical path to faster-than-light travel that does not immediately shatter the laws of physics. It does not rely on imaginary particles, paradoxes, or hand-waving assumptions. Instead, it uses the very fabric of space-time itself as the medium of travel. Relativity tells us that space and time are not rigid, but flexible. The universe itself has already demonstrated this in cosmic inflation. The warp bubble is, in essence, an attempt to harness that same principle on a smaller scale. Some researchers continue to refine the idea, looking for ways to reduce the energy demands or connect the concept to effects that might one day be tested. In 2012, physicist Harold White suggested a modification to the warp bubble's shape that could, in theory, cut the energy requirement dramatically from cosmic scales to something closer to the mass energy of a large planet. Still far beyond anything we can hope to achieve, but an enormous improvement nonetheless. Such work keeps the concept alive in scientific discussion, even if it remains firmly out of reach. If such a device were ever built, it would change humanity's place in the universe forever. Stars that are now unreachable would suddenly lie within our grasp. The boundaries of the observable universe would no longer be fixed by the speed of light, but by our ability to generate and control warp bubbles. Yet at the same time, the dangers and unknowns remind us of how fragile our grasp on physics truly is. What seems possible in equations can be treacherous in reality, filled with hidden costs and risks we do not yet understand. The Alcubierre drive represents the human desire to break free of limits, to find a loophole in the rules that bind us to one corner of the galaxy. It shows how creative thinking can push science into new territory, even when the practical barriers look insurmountable. It sits on the edge between dream and reality, reminding us that the laws of physics are not just obstacles, but also sources of inspiration. Negative energy and exotic matter. Ingredients. No one knows how to cook. Unlike the familiar matter that makes up stars, planets, and people, exotic matter would have the strange property of negative energy density. In other words, instead of adding mass and gravity to the universe, it would subtract them. It would push space away instead of pulling it in. This might sound impossible, but the equations that describe space-time can be solved in such a way that negative energy appears as a requirement for certain configurations. A traversable wormhole, for instance, is only stable if exotic matter threads its throat, keeping it from collapsing under the weight of its own gravity. Likewise, the warp bubble imagined by Alcubierre needs a shell of negative energy around it. Without this strange ingredient, the bubble cannot form, and the idea of shortcutting across the galaxy dies before it begins. So the natural question becomes, does negative energy exist, even in the smallest amount? Physicists point to certain quantum effects as hints that it might. The most famous example is the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they experience a tiny force pulling them inward. This happens because the quantum vacuum is not empty. It seethes with energy fluctuations. Between the plates, only certain wavelengths can exist, while outside the plates, all wavelengths are allowed. The imbalance creates a pressure difference, and the plates are pushed together. This force can be measured, and in some interpretations, it can be thought of as a manifestation of negative energy density between the plates. The Casimir effect is real, but the amount of negative energy it seems to reveal is minuscule, so small that it is useless for engineering purposes. It cannot be gathered in buckets, nor scaled up to hold open a wormhole. It flickers in and out as part of the restless nature of the quantum vacuum. If exotic matter exists in the universe, it hides itself well, appearing only as whispers at the edge of our instruments. Another path physicists consider is through the concept of quantum fields and the uncertainty principle. According to quantum theory, energy levels can briefly dip below zero in tiny regions of spacetime. These are temporary violations that are allowed as long as they vanish quickly. For example, a particle and its antiparticle can pop into existence, borrow energy from the vacuum, and then annihilate each other, repaying the debt in a fraction of a second. During that fleeting instant, negative energy may play a role. Yet once again, the amounts are so small and so temporary that they cannot be harnessed in any practical way. It is like trying to capture the wind by grabbing at the air with your bare hands. Still, theoretical studies show that if exotic matter could be stabilized and amplified, it might serve as the scaffolding for futuristic space-time engineering. It would hold open tunnels through space, wrap around warp bubbles, and even allow controlled manipulations of gravity. But every equation that predicts its usefulness is matched by another that shows how fragile and unstable it would be. The very act of trying to concentrate negative energy might cause it to evaporate, slipping away before it can be put to work. Adding to the puzzle, exotic matter does not play by the normal rules of physics. Regular matter has positive mass, positive energy, and produces attractive gravity. Exotic matter, on the other hand, would produce repulsive gravity. It would push objects away instead of pulling them together. That sounds useful for building warp drives, but it also raises deep questions. If negative energy were common or easily produced, the universe as we know it might not even exist. Stars might not form, galaxies might not hold together, and planets might drift apart. The fact that we live in a universe filled with stable structures suggests that exotic matter, if it exists, must be incredibly rare and hard to find. When physicists talk about exotic matter, they are often stretching the definitions of energy and mass beyond their familiar meanings. In everyday life, energy is something that powers engines or lights up cities. In physics, energy is more abstract. It is a conserved quantity that appears in equations of motion and field theory. Negative energy, then, may not be a substance that can be bottled or extracted. It may simply be a mathematical trick, a way of describing certain effects without implying that a new form of matter actually exists. If this is true, then the dream of exotic matter as fuel for starships is just that, a dream. Still, science thrives on imagination. Even though exotic matter has never been observed in usable form, researchers continue to test the edges of quantum mechanics for any hint that it might be real. High-energy experiments, particle accelerators, and precision measurements of the vacuum all contribute small pieces of the puzzle. Every unexplained anomaly, no matter how tiny, is studied for signs of negative energy effects. Most turn out to have mundane explanations, but the search continues. There are also many physicists who warn that the need for exotic matter is a sign that concepts like warp drives and traversable wormholes may not be physically achievable. They argue that if your theory requires an ingredient that cannot exist in nature, then your theory is not a real blueprint for the future. Instead, it is an exploration of mathematical possibilities. In this view, exotic matter belongs to the same category as perpetual motion machines. Fascinating to think about, but forever out of reach. Still, one cannot help but notice that physics has a long history of turning impossibilities into realities. There was a time when heavier-than-air flight was dismissed as fantasy, when nuclear energy seemed unattainable. Could exotic matter be another example waiting for its moment? Or is it truly the barrier that no amount of technology or cleverness will ever overcome? Cosmic strings and faster-than-light, FTL, highways through the early universe. Cosmic strings are thought to be defects in the structure of the universe itself, scars left over from the earliest moments after the Big Bang. Just as cracks can form in ice as it freezes or wrinkles can appear in metal as it cools, space-time itself may have developed imperfections as it expanded and cooled during those first fractions of a second. These imperfections, if they exist, would take the form of unimaginably thin but enormously long filaments, stretching across the cosmos. They would be older than galaxies, older than stars, older than atoms. They would be among the most ancient objects in existence. What makes cosmic strings so fascinating is not just their age, but their possible power. A cosmic string would be incredibly dense. A piece of one just a kilometer long could outweigh a planet. Yet despite their density, they would be thinner than a proton, so thin that they would not look like physical objects at all. They would instead reveal themselves through their gravitational effects. A cosmic string would pull on space-time, warping it in ways that differ from the familiar pull of stars and planets. Instead of attracting mass toward a center, as a planet does, a cosmic string would distort space in a wedge-like fashion. Moving around one would feel less like orbiting a body, and more like sliding along the seam of reality itself. This distortion is what gives rise to the idea of shortcuts. According to Einstein's relativity, a cosmic string could create what is known as a deficit angle in space. Imagine cutting a slice out of a sheet of paper and then taping the edges together. The surface would look mostly the same, but if you walked around the taped seam, you would find that you had traveled a shorter distance than expected. Space around a cosmic string works in a similar way. Paths near the string could allow a traveler to cover enormous cosmic distances more quickly than light traveling through normal space. To an observer far away, it would look as if you had jumped ahead, skipping part of the journey. Physicists have speculated that if two cosmic strings moved relative to each other, the distortions they create might even allow for effective faster-than-light travel. In certain alignments, the geometry of space could, in theory, permit a closed path where a traveler returns to their starting point sooner than light would. Light still obeys its local speed limit, but the geometry itself creates the illusion of breaking it. In this way, cosmic strings have been imagined as natural highways through the cosmos, relics of the early universe that might one day guide journeys to distant stars. Of course, this picture is filled with uncertainty. For one, cosmic strings have never been observed. They remain theoretical objects, predicted by some versions of high-energy physics, but absent from the evidence we can measure. Astronomers have searched for them indirectly, looking for the gravitational lensing they would cause. A cosmic string passing in front of distant galaxies would bend their light into sharp, unusual patterns, unlike the gentle arcs produced by ordinary gravity. So far, no clear examples have been found. Some hints appear in data, but they vanish under closer study. If strings exist, they may be rare or scattered in ways that make them hard to detect. Even if they are real, the practical challenge of using them as highways is enormous. Their gravity would be extreme, far stronger than anything we could safely approach with current technology. Moving close enough to a string to take advantage of its shortcut could mean venturing into tidal forces that would rip apart any known material. In other words, the very thing that makes cosmic strings useful as roads might also make them deadly obstacles. To imagine them as routes across the stars requires not just the discovery of their existence, but also the invention of technologies that can endure their crushing environment. If strings are there, they are like hidden interstellar highways waiting to be mapped. A civilization advanced enough to control its movement near them could, in principle, leap across galactic distances. Instead of taking millions of years to cross the Milky Way, travel could be reduced to manageable spans. One can imagine starships navigating a network of strings, much as ancient sailors once relied on trade winds and currents to move across oceans. The strings would be the deep cosmic currents, not made of air or water, but of bent spacetime itself. Some theories suggest that if strings intersected or vibrated, they could create loops or cusps, regions where energy density spikes. These regions might radiate gravitational waves or produce bursts of particles. Others speculate that the intersection of strings could open pathways similar to wormholes. In this way, strings are not just highways, but also potential gateways. These defects would not have been designed, they would not be intentional, they would simply be leftovers from the universe's birth, scars in the fabric of reality. And yet, to us, they might appear as if they were placed deliberately, like bridges between faraway lands. If the universe does contain such features, does it hint at a deeper design? Or is it simply another case of humans projecting purpose onto natural phenomena? Even in the absence of evidence, scientists continue to run simulations to test how strings would behave and to calculate the possibilities of travel near them. They do so not because they expect to build such highways tomorrow, but because the mathematics of cosmic strings reveals something fundamental about how space-time might behave under extreme conditions. If strings exist, they would be the closest thing we have to natural engineering at a cosmic scale. They would not just be curiosities, but the raw infrastructure of a universe that still holds secrets from its earliest days. Perhaps one day, an astronomer will notice a strange lensing pattern, a sharp line of light splitting the sky in a way no galaxy or star could explain. That discovery would mark the first step toward charting these ancient relics. And from there, the dream of turning them into interstellar roads would no longer be confined to speculation. It would become part of the human map of the cosmos. Traversable wormholes, folding reality into a shortcut. Imagine, instead of spending thousands of years crossing interstellar space, you could step through a tunnel and arrive instantly on the other side. At their heart, wormholes are not a rejection of Einstein's relativity, but an extreme use of it. The same equations that describe black holes also allow solutions where space-time curves back on itself, linking two distant regions with a bridge. In the mathematics, nothing forbids such structures. The problem is whether the universe actually allows them to exist in reality. The basic idea of a wormhole can be pictured as folding a sheet of paper. Imagine two dots on opposite ends of the paper, representing two distant stars. To travel from one dot to the other across the surface would take time. But if you fold the paper so the dots touch, the distance vanishes. A wormhole is the cosmic version of this fold. where space-time itself bends so two faraway regions connect through a tunnel. From the inside, the tunnel might look like a throat or passage. From the outside, it could appear as a sphere, a shimmering gateway. The theory is straightforward, but the physics quickly becomes messy. Wormholes are unstable by nature. Left alone, the immense gravity pulling inward would cause the throat to collapse faster than anything could pass through. They would pinch shut, trapping light and matter before they could cross. This is where exotic matter enters the story. To hold a wormhole open, you would need a kind of material that exerts negative pressure, pushing outward against the collapse. Normal matter only pulls inward. Exotic matter would push outward, counterbalancing the gravity of the throat. Without it, traversable wormholes remain nothing more than mathematical curiosities. To stabilize even a tiny wormhole, you would need amounts of exotic matter on astrophysical scales, far beyond what humans can currently dream of producing. Even if the exotic matter problem could be solved, wormholes raise other difficulties. One is size. Theoretical wormholes could be microscopic, forming and disappearing within fractions of a second in the froth of quantum space. To make one large enough for a person, a ship, or even a signal to pass through would require stretching it far beyond its natural scale. That again demands not only exotic matter, but also a way to control and enlarge a phenomenon we have never seen. Another problem is stability during passage. The walls of a wormhole might bombard travelers with intense radiation, or tidal forces could rip apart any craft that tried to enter. There is also the question of where wormholes lead. In theory, they could link two distant points in space, two different times, or even two separate universes. If they connect across time, they immediately raise the specter of paradox. Traveling through such a tunnel could let you arrive before you left, breaking causality. If they connect to other universes, they could expose travelers to physics we do not understand or cannot survive. From a scientific point of view, these possibilities are both fascinating and alarming. They show how much we do not know about the deep structure of space-time. Despite the obstacles, wormholes are not dismissed entirely. Physicists treat them as valuable thought experiments. They force us to test the limits of relativity, quantum theory, and cosmology. By asking whether wormholes could exist, scientists uncover new insights into the nature of energy, gravity, and the fabric of the cosmos. In recent decades, some researchers have even tried to design wormholes on paper that are more stable than the early models. These involve clever geometries or additional fields that might reduce the need for exotic matter. None of these ideas solves the problem completely, but they show that the door is not closed. On the experimental side, there is no evidence that wormholes exist. No telescope has spotted one, no signal has hinted at their presence. But scientists have proposed ways to search indirectly. A wormhole might distort light passing near it in unique ways, creating lensing patterns unlike those caused by galaxies or black holes. It might even allow unusual echoes of signals as light passes through the throat and returns. Detecting such signatures would be extraordinarily difficult. But the possibility adds one more target to the long list of cosmic mysteries astronomers are hunting. If wormholes ever move from theory to practice, they would change everything about how we see the universe. The distance between stars would no longer be a fixed obstacle. Exploration would not depend on rockets or even warp drives, but on the ability to locate, open, and stabilize tunnels through space-time. The Milky Way could become a network of doors, each linking worlds that would otherwise remain out of reach. Civilizations could spread not by crawling through the stars, but by stepping across the folded fabric of reality. Of course, this vision lies far beyond current science. For now, wormholes remain symbols of possibility rather than blueprints for action. They sit at the edge of physics, waiting to be proven impossible, or against all odds, revealed as the universe's hidden roads. Quantum foam as a potential superluminal playground. At the deepest levels of the universe, far smaller than atoms, protons, or even quarks, lies a realm that physics can only describe with imagination and mathematics. It is here that the concept of quantum foam arises. The idea comes from attempts to unite quantum mechanics with general relativity. According to John Wheeler, who first popularized it, space-time itself may not be smooth and continuous as it looks on large scales. Instead, when examined at scales of the Planck length, about 10 to the power of -35 meters, it might look like a restless, ever-changing sea. Tiny fluctuations of energy, appearing and vanishing in unimaginably small timescales, could twist space-time into miniature bubbles, tunnels, and folds. To us, the universe looks calm and predictable, but at this invisible level, reality might be frothing like boiling water. Some theorists suggest that wormhole-like structures could be constantly forming and collapsing within this foam. Each one would be absurdly small, far smaller than the nucleus of an atom, and they would open and close almost instantly. But if an advanced civilization could somehow stabilize one of these tunnels, even for a fraction of a second, they might expand it into something large enough to pass through. In that sense, the quantum foam could be thought of as a natural network of hidden pathways linking different regions of the universe. To us, these connections are unreachable, but to a species far ahead of us in technology, they could be the cosmic highways science fiction often imagines. Of course, stabilizing one of these fluctuations would not be simple. Still, the notion that space-time itself might be riddled with tiny connections has been enough to inspire physicists to take the possibility seriously, at least on paper. If we take the idea further, the quantum foam could be seen as a kind of interstellar lottery system. Every fluctuation of spacetime might create a potential connection to somewhere else. The vast majority would vanish before anything could use them. But if even one could be stabilized, it could provide a direct link across light years. In this sense, advanced beings might not build faster-than-light ships in the way we picture, with engines and thrusters, but instead fish within the quantum foam, searching for the right kind of tunnel to exploit. A ship could enter one point in space, slip through the fabric at the microscopic level, and emerge instantly in another star system. The challenge, of course, is scale. The Planck length is so small that it dwarfs anything we can currently measure, let alone manipulate. Our most powerful particle accelerators probe down to levels far above this realm, but they are still nowhere near the energies required to see what quantum foam really looks like. Even with the most advanced instruments, space-time appears smooth and continuous, as though the underlying froth is hidden behind an impenetrable veil. Some physicists suggest that new theories of quantum gravity, such as string theory or loop quantum gravity, might eventually describe this hidden layer in detail. But until then, the idea of tunneling through quantum foam remains in the domain of speculation. There's also the question of what would happen to something passing through such a tunnel. Space-time at this scale is not a gentle place. It is chaotic, unstable, and violent. A ship or even a particle trying to traverse a raw fluctuation might be torn apart instantly. The walls of the tunnel could collapse faster than light itself can respond, leaving no chance of survival. To make quantum foam useful for travel, one would need not just a way to find these tunnels, but also a way to tame their instability. That might mean surrounding them with stabilizing fields, anchoring them with negative energy, or bending space-time on larger scales to create a shell around the passage. If civilizations do reach the stage of manipulating quantum foam, their technology would be beyond anything we can imagine. They might see the universe less as a vast, empty expanse, and more as a dense lattice of hidden connections, like a spiderweb woven into the very fabric of space-time. For them, jumping across galaxies could be as trivial as stepping through a doorway. To us, this sounds like fantasy, but from a physics perspective, it is simply the extrapolation of rules we don't yet fully understand. The foam is already predicted by quantum field theory and relativity. It is not an invention, but a natural consequence of their marriage. The leap is in imagining how it could be harnessed. It's worth noting that quantum foam has been considered not just for travel, but also for communication. If space-time fluctuations naturally link distant regions, then in theory, signals could tunnel through them, bypassing the light-speed barrier. Would such communication allow messages to arrive before they were sent, creating paradoxes? Would the instability of the foam scramble the signal beyond recognition? There's also the risk that the foam, if ever probed directly, might be far stranger than we imagine. Some speculative theories propose that the quantum froth could act like a cosmic sensor, destroying any attempt to stabilize a tunnel before it becomes usable. In that sense, the universe itself might enforce the light speed limit, not with a wall, but with a seething mess of self-destructing shortcuts. It could be that quantum foam is not an invitation to travel, but a natural safeguard, ensuring that causality and the flow of time remain intact. If space-time is indeed built on a foundation of restless fluctuations, then somewhere in that turbulence might lie a door, one that has not yet closed, one that could be widened, one that could take us where no rocket ever could. Whether that door is reachable or forever beyond us remains unknown. But in the play of foam at the bottom of reality, some see a hint of the universe whispering that faster-than-light travel, though forbidden on the surface, might be hidden in its depths. Could empty space be engineered for speed? If space itself is not a blank backdrop, but an active medium, then perhaps it can be shaped or manipulated. The same way air can be compressed or water can be channeled, the vacuum might have properties that can be altered. Some theories suggest that if we could tap into this hidden reservoir of energy, we might be able to bend or stretch space in ways that get around the light speed barrier. If such control were possible, one application could be to alter the permittivity of space, the property that determines how fast light travels through it. Normally, this value is fixed and the speed of light remains constant. But if advanced technology could change the vacuum's characteristics, then light might move differently in engineered regions. A spaceship inside such a region might appear to move faster than light to outside observers, even though locally, the laws of physics would not be violated. This is a subtle way of bypassing the cosmic speed limit, not by breaking it, but by redefining the track on which the race is run. Theoretical calculations suggest that the vacuum holds an immense amount of energy, so much that even a single cubic centimeter contains more potential than all the visible stars combined. But this is energy in a form we cannot easily extract. It is locked in balance, cancelling itself out in ways that leave only faint traces like the Casimir effect. The challenge is not that the energy isn't there, but that it is like water trapped in ice. Present, but inaccessible, without the right method of release. Physicists sometimes describe this as the universe sitting on a vast ocean of power that we cannot yet touch. There is also a danger in imagining what might happen if we did learn to access it. If vacuum energy could be altered or drained, the effects might ripple outward in ways beyond control. Some fear that tampering with the zero-point field could destabilize the very fabric of space-time. Since it underlies all of existence, a small change might not remain local. It could spread, reshaping the laws of physics across vast regions. For now, this is only speculation, but it highlights why ideas about vacuum manipulation are treated with both excitement and caution. If space itself could be engineered, then faster-than-light travel might shift from impossible to simply difficult. A warp bubble, for example, might be powered by carefully altering vacuum energy, expanding it behind a ship and contracting it ahead. High-intensity lasers, particle accelerators, and quantum field experiments are pushing the boundaries of how energy interacts with space. Though none of these tools come close to manipulating vacuum energy on a useful scale, they do confirm that the vacuum is dynamic, not dead. If empty space is not truly empty, then the speed of light itself may not be as final as it seems. The barrier exists within the framework of our current vacuum, with its fixed constants and properties. But if those properties can be changed, then perhaps the barrier can be bent as well. The universe, in this view, becomes more like a flexible stage than a rigid cage. The cosmic speed limit still stands in the play we are familiar with, but it may not be permanent if we learn to rewrite the script. Skeptics counter that such hopes may be misplaced. They argue that the vacuum's energy is not a resource to be mined, but a mathematical feature of our theories, a way to describe fluctuations that cancel out. To them, the Casimir effect and similar phenomena do not point toward usable power, but toward the limits of our models. The vacuum may be busy on paper, but in practical terms, it may always remain unreachable. If they are right, then vacuum manipulation will forever stay a dream. Why breaking light speed might break time itself. As you approach the speed of light, time slows down compared to someone standing still. This has been measured many times with fast-moving particles, and even with satellites orbiting Earth. The closer you get to the light speed barrier, the more time bends. And if you were to go beyond it, the rules suggest that time might stop making sense. One of the most unsettling predictions is that faster-than-light travel could allow events to unfold in reverse order. Imagine sending a signal to a distant star that moves faster than light. In one frame of reference, the signal leaves after you press the button and arrives later, as expected. But in another frame, the equations allow for the possibility that the signal arrives before you even press the button. In other words, the effect comes before the cause. This kind of situation is called a causality violation. Break causality, and it is hard to say what is left. According to Einstein, there is no universal viewpoint in the universe. Instead, every observer measures time and space differently depending on their speed. This usually works smoothly because the speed of light acts as a boundary that keeps all viewpoints consistent. But if something goes faster than light, one observer might see it moving forward in time, while another sees it moving backward. Both are equally valid under the rules of relativity, which means there is no way to decide which version is correct. That kind of contradiction is deeply troubling. It suggests that faster-than-light motion may tear apart the logical fabric of time. The consequences of such contradictions are dramatic. It opens the door to paradoxes, like the famous grandfather paradox, where someone could, in theory, prevent their own existence by killing their grandfather before he has any children. In physics, this kind of logical loop is treated as a warning sign. It suggests that nature itself must have built-in defenses against such outcomes. Quantum entanglement, tunneling, and other strange effects can seem to move faster than light at first glance. Yet every time researchers dig deeper, they find that information never actually outruns light. The universe seems to police itself, ensuring that causality stays intact. Even when it looks like a loophole might exist, closer inspection shows that the timeline remains safe. There are attempts within physics to see if the paradoxes could be avoided. Some models suggest that faster-than-light travel might be possible in limited circumstances if the universe somehow self-consistently closes the loop. In these ideas, you could go back in time, but only in ways that do not create contradictions. For instance, you might interact with the past, but your actions would already be part of history, so you could not change the outcome. This is sometimes called the principle of self-consistency. While intriguing, it remains speculation. No experiment has shown that nature allows such a compromise. Another possibility comes from the idea of parallel timelines. Some theorists argue that if faster-than-light motion did occur, it might send you into a different branch of reality rather than back into your own past. In that case, causality would remain intact in your timeline, but you would find yourself in another version of history. This concept fits neatly with certain interpretations of quantum mechanics, but it raises as many questions as it answers. If infinite timelines exist, then FTL might simply shift you between them. What is clear is that faster-than-light travel and causality are tied together in a way that cannot be separated. You cannot have one without facing the other. The cosmic speed limit does not just protect physics, it may protect time itself from unraveling. The thought of ships or messages racing past light is thrilling, but the cost might be the collapse of the orderly chain of cause and effect. That chain is what gives meaning to every event in the universe. To risk breaking it is to risk breaking reality. Closed time-like curves, the universe's loopholes for paradoxes. When scientists first began to explore the mathematics of Einstein's theory of relativity, they discovered something strange, hiding in its equations. Space-time could bend, twist, and fold in ways that weren't at all like the flat, straight world we imagine in everyday life. Most of these possibilities seemed exotic, but still logical. Black holes that trap light, wormholes that might connect distant regions, and the expansion of the universe itself. But some solutions looked far stranger. They hinted at the possibility that space-time could allow closed, timelike curves. These are paths through the universe that, instead of moving forward into the future, eventually bring you back into your own past. The name timelike comes from relativity, where paths in space-time can be classified as space-like, light-like, or time-like. A time-like path is one that could be taken by a person or an object traveling slower than the speed of light. Normally, if you follow a time-like path, you go from the present into the future, step by step, second by second. But if the path is closed, like a circle, then after enough travel, you don't arrive in the future at all. You arrive in your own past. This is the essence of a closed, time-like curve, a loop in time where events repeat and where cause and effect start to blur together in unsettling ways. One of the first hints of such curves came from the work of the Austrian physicist Kurt Gödel in the 1940s. Better known for his incompleteness theorem in mathematics, Gödel also explored solutions to Einstein's equations. He found one describing a universe that rotated as a whole. In this rotating cosmos, it was possible to follow a path that would eventually loop back in time. That meant a person could, in theory, travel into their own past without ever exceeding the speed of light. Gödel himself admitted this was strange, but he insisted that the math was solid. His solution became one of the earliest examples, showing that relativity did not completely forbid time travel. Gödel's rotating universe wasn't the only scenario. Later work found other setups that could generate closed time-like curves. Wormholes could do it, if one mouth of the wormhole experienced time differently than the other. Imagine one entrance near Earth, and the other carried on a spaceship traveling close to light speed. Because of time dilation, the moving mouth would age differently than the stationary one. Step through, and you might emerge at an earlier moment. In effect, the wormhole becomes not just a bridge through space, but a bridge through time. If two cosmic strings passed near each other and moved at high speed, the geometry around them might allow a shortcut into the past. Again, the strange possibilities emerge not from breaking physics, but from following its equations to their logical extremes. The trouble, of course, is that these loops in time create paradoxes. If you can return to your own past, what stops you from changing it? Could you give yourself information from the future, creating knowledge without origin? These are the classic time travel paradoxes, and closed time-like curves sit right at the heart of them. If nature allows these loops, then causality begins to unravel. Physicists have tried to grapple with this in different ways. Some argue that nature has a built-in rule that prevents paradoxes. This is sometimes called the Novikov self-consistency principle. It suggests that if time travel is possible, then whatever happens on a closed time-like curve must be consistent with history. You can go back and interact with the past, but you cannot change it in a way that produces a contradiction. For example, you might try to stop your younger self from making a choice, but in the end, your actions would be part of the reason that choice was made. History bends, but never breaks. Other scientists propose that paradoxes could be avoided by branching timelines. In this view, when you travel into the past, you don't alter your own history, you create a new one. Each change causes the universe to split into multiple versions. You cannot erase your own origin, but you might spin off into a different reality, where events unfold differently. This idea fits neatly with the many worlds interpretation of quantum mechanics. If true, it would mean closed time-like curves do not trap us in contradictions, but instead open up countless alternate histories. There's also a more skeptical view, that nature simply forbids these loops from forming in the first place. This idea, sometimes called chronology protection, was famously suggested by Stephen Hawking. He argued that even if relativity's equations allow time loops in theory, quantum effects might prevent them in reality. For instance, if you tried to build a wormhole that functioned as a time machine, radiation could pile up in such a way that it destroyed the wormhole before it could be used. The laws of physics, in this view, conspire to protect causality. The debate is far from settled. On one hand, relativity leaves the door open to closed timelike curves. On the other hand, quantum mechanics may slam it shut. Because we lack a full theory of quantum gravity, a single framework that unites the large-scale geometry of relativity with the small-scale rules of quantum physics, we cannot yet know for certain. Closed timelike curves sit right at this intersection, making them both fascinating and frustrating. What makes the idea especially eerie is how normal it would feel to anyone inside such a loop. Imagine boarding a spaceship and setting off on a journey. From your perspective, everything proceeds smoothly. You accelerate, coast, and follow a path through space. Eventually, you return to a planet that looks familiar. Only then do you realize it isn't just familiar. It is Earth, and the date is decades before you left. You haven't broken any rules as far as your local experience is concerned. You simply followed a path through space-time. The strangeness only shows up when you compare your timeline with everyone else's. Even stranger, closed timelike curves could lead to situations where events repeat endlessly. Imagine a particle moving along such a loop. It would trace the same path again and again, with no beginning and no end. In a way, the universe would contain regions where time does not flow forward in the usual sense, but circles back on itself forever. This is hard to reconcile with our ordinary sense of progress, of past giving way to present and future. It raises unsettling questions about free will and determinism. If events on such loops are fixed and self-consistent, then everything that happens there is unavoidable. The concept of choice may vanish entirely. Studying closed timelike curves pushes us to clarify what we mean by time, cause, and effect. It forces us to test the limits of relativity and to imagine what a deeper theory might look like. Even if these curves never exist in our universe, the fact that the equations allow them tells us that our understanding of time is incomplete. The rules that feel so obvious in daily life may be fragile when stretched to cosmic extremes. Closed timelike curves could be real features of the universe, hidden in some corner of space-time we haven't yet explored. Or they could be mathematical mirages, artifacts of incomplete equations that will vanish when we finally merge relativity with quantum mechanics. Either way, they remind us that time, the most ordinary thing we know, is still one of the deepest riddles in physics. Multiverse spillover, a way to save causality without killing FTL. The multiverse solution is the thought that each paradox is resolved not by breaking the laws of physics, but by shifting into another universe where both outcomes can exist without contradiction. To understand this, it helps to picture time as a branching tree rather than a single unbroken line. In ordinary life, we assume that events happen in sequence, one cause, one effect, with no room for alternatives. But what if every possible choice, every possible outcome, actually exists somewhere? In that picture, the world you see is only one branch, while countless others stretch out unseen. A paradox only arises if you try to cram all possibilities into a single line of history. If you allow many lines, then faster-than-light travel, and even time travel, no longer threaten causality. They simply shift you from one branch to another. In quantum physics, particles don't have a single definite state until they are measured. Instead, they exist in a cloud of possibilities, described by a wave function. When you observe them, the wave function seems to collapse into one outcome. The many worlds idea says that collapse never really happens. Instead, all outcomes occur, each in its own branching universe. The world you see is just one thread in this vast cosmic weave. Now imagine applying this to faster-than-light travel. Suppose you build a starship that can leap across light years in an instant. When you jump faster than light and risk arriving in your own past, you instead slide into a different branch where your arrival and departure can both make sense. Your original timeline continues untouched, while you step into another that now includes your appearance. This solution has an elegant appeal because it preserves both possibilities. The paradox of meeting yourself before you leave dissolves once you accept that there are multiple versions of you, each on a slightly different path. In one branch, you stay behind and board the ship. In another, you suddenly appear, having just arrived by faster-than-light travel. Neither branch breaks causality because neither has an internal contradiction. They simply coexist in a larger multiverse. Causality remains intact within each branch of reality, while faster-than-light travel becomes a mechanism for jumping between them. Instead of paradox, you get proliferation, an ever-expanding set of timelines, each consistent within itself. There are, of course, difficulties with this idea. For one thing, we have no experimental proof that the many worlds interpretation of quantum mechanics is true. It is one of several ways to understand the strange rules of the quantum world, and while many physicists find it appealing, others prefer rival explanations. Still, if all outcomes happen, then probability, quantum measurement, and paradoxes of time and causality all find a place in the larger picture. Another challenge is that the multiverse is, by definition, hard to detect. If each branch is separate, then how could we ever measure or interact with the others? Some theorists argue that interference patterns in quantum experiments already hint at many worlds operating in the background, even if we cannot touch them directly. Others suggest that exotic physics, such as wormholes or quantum entanglement on cosmic scales, might allow limited crosstalk between branches. If faster-than-light travel itself requires tapping into such exotic physics, then perhaps spillover between universes is not as far-fetched as it sounds. What if faster-than-light travel is only possible because of the multiverse? Perhaps when you exceed light speed, you automatically leave your own branch of reality and enter another. What seems like jumping across space in an instant may actually be slipping into a neighboring universe where the journey is already complete. In that case, FTL travel would never break causality because it is not movement within a single universe, it is movement between universes. The price of outrunning light would be shifting realities. Such a scenario would mean that each FTL trip creates a kind of fork. In one branch, you stayed behind, never breaking the speed barrier. In another, you arrived far away, faster than light would allow in your original world. Each branch is self-consistent, so there is no paradox. But the cost is that you can never truly return to the same world you left. You can reach one that looks identical, with the same people and the same history up to a point, but technically it would always be a slightly different branch. This raises profound questions about identity, memory, and belonging. If you arrive in a universe where your other self still exists, which one is really you? The multiverse spillover idea also reframes how we might think about information. If sending signals faster than light inevitably shifts them into another branch, then you cannot use them to alter your own past. You can only influence another version of events in another universe. This could preserve the absolute safety of causality, while still allowing communication that leaps beyond light speed limits. The paradoxes vanish, but the strange side effect is that you are never really talking to your own world. You are always whispering to another. If the multiverse exists, then every possible outcome of every event already plays out somewhere. In that sense, paradoxes are not mistakes in logic, but doorways into alternative branches. The multiverse doesn't fix contradictions by preventing them. It absorbs them, distributing them across countless realities. Faster-than-light travel would simply be one more way of exploring that endless landscape. The imagery this creates is striking. Instead of a single timeline stretched out like a ribbon, reality becomes more like a vast forest of paths, constantly splitting and multiplying. Every decision, every quantum fluctuation, every faster-than-light leap adds new branches. If this is true, then the cosmos is far richer and stranger than anything we see on the surface. Our familiar world is just one leaf on a much larger tree. And faster than light travel might be the wind that lets us hop from one leaf to another. Yet despite its elegance, the multiverse solution is not without critics. Some argue that it multiplies realities needlessly, creating an infinite number of unseen worlds to solve problems that may not exist. Others say it raises more questions than it answers. If new universes are created, where do they come from? How are they stored? Do they require energy, space, or resources, or are they simply mathematical possibilities? Without clear answers, the multiverse remains as much philosophy as physics. Still, the appeal is undeniable. Instead of forbidding faster-than-light travel, the multiverse spillover idea offers a compromise between the dream of outrunning light and the need to preserve logical order. Chronology protection, the universe fighting back against time travel. Stephen Hawking's chronology protection conjecture may sound technical, but the core thought is simple. Nature itself might prevent time paradoxes by shutting down any path that could allow them. In other words, even if you had the technology to bend space-time or jump faster than light, the laws of physics might quietly interfere before you could ever create a contradiction. The idea of chronology protection means that while equations in general relativity allow strange structures like wormholes or closed timelike curves, something deeper might always prevent them from being usable. For example, if you tried to stabilize a wormhole long enough to send a message back in time, quantum effects might pile up and collapse it before anything paradoxical could happen. If you attempted to accelerate a spacecraft into a path that would loop back into its own history, the energies required might diverge toward infinity, making it physically impossible. One way to picture this is to think of the universe as having guardrails. On a mountain road, you can steer left or right, but the rails keep you from tumbling over the edge. In the same way, relativity, quantum mechanics, and energy limits might allow us to experiment with extreme physics, but slam down barriers the moment we try to cross into paradox. Hawking liked to joke that chronology protection made the world safe for historians. His humor aside, the point was serious. History might be locked in place, not by human law, but by cosmic law. This doesn't necessarily mean faster-than-light motion is impossible. It only suggests that if it ever becomes real, it will never create situations where you can meddle with your own past. Perhaps a warp drive, wormhole, or quantum trick could take you across the galaxy in an instant, but not in a way that lets you arrive before you departed. The moment such a risk appeared, some hidden process would intervene to stop it. That intervention could be subtle, like tiny fluctuations that destabilize the effect, or dramatic, like radiation bursts that destroy the experiment. In every case, paradox would be avoided. There are hints in current physics that support this possibility. One comes from quantum field theory, which suggests that when space-time is distorted in extreme ways, the vacuum is not quiet. Instead, particles pop into existence, filling the space with energy. This buildup could grow so intense that it shuts the wormhole before anything passes through. Another hint lies in the energy requirements of exotic spacetimes. The closer you come to creating a path that could allow time loops, the more outrageous the negative energy you need. That energy might simply not exist in quantities large enough to ever succeed. In this way, the laws of nature themselves create a firewall against paradox. Chronology protection is not proven. It is more of a guiding principle, a belief that the universe must be internally consistent. Some physicists argue that without such protection, the contradictions are too severe to make sense of. Others counter that maybe paradoxes are not as destructive as we think, or that multiverse branching can resolve them without forbidding the underlying physics. Still, Hawking's conjecture has a strong pull because it fits with a deeper intuition that reality is not fragile. It resists self-destruction. There is also something comforting in the idea. If the universe guards its own history, then time is not as easily broken. You cannot undo events, erase mistakes, or rewrite outcomes just by flying fast enough or finding a clever loophole. The arrow of time remains fixed, at least within the world you inhabit. This doesn't erase the dream of exploring faster-than-light travel, but it reshapes it. Instead of a tool for rewriting the past, it becomes a tool only for moving forward into the future, even if at extraordinary speeds. If nature blocks paradoxes, how exactly does it do it? Are there hidden laws of quantum gravity that step in? Does the vacuum itself explode with particles when danger approaches? Is there a cosmic censor that keeps certain events from ever being observed? These are not trivial details. They cut to the heart of how space-time and quantum theory fit together. Without a complete theory of quantum gravity, we cannot say for sure. Chronology protection is less a finished answer and more a clue about what a final theory might require. Some theorists speculate that chronology protection might be an emergent effect, not a built-in law. In this view, the universe doesn't need a special rule to forbid paradoxes. Instead, paradoxical situations simply destabilize themselves, collapsing under their own contradictions. It's not that the universe says no. It's that paradoxes can't hold together in the first place, like a building designed on flawed blueprints. Try to construct one, and it falls apart before completion. There is also the possibility that chronology protection works selectively. Maybe certain exotic spacetimes could exist, but only in limited forms that never allow true paradox. A wormhole, for instance, might let you cross space instantly, but not time. A warp bubble could bend spacetime to shorten journeys, but never permit you to arrive before you left. In this case, faster-than-light travel would survive, but the rules would always steer it away from the dangerous territory of backward time travel. This perspective changes how we think about the quest for faster-than-light travel. Instead of asking, is it possible at all, we might instead ask, how does the universe allow it while still protecting causality? That shift frames the problem differently. It suggests that if we do someday discover faster-than-light methods, they will be tightly constrained by hidden safety nets. We might build engines that warp spacetime or discover natural wormholes, but their operation will always bend toward preserving order. For explorers of the cosmos, that might be a blessing. It means we could cross unimaginable distances without tearing history apart. It means our journeys would be daring, but not destructive to the fabric of time. It also means that if faster-than-light travel ever enters reality, it may look far stranger than the straightforward machines of sci-fi. The designs we imagine today, sleek starships streaking across the galaxy, may be replaced by contraptions shaped by the demands of chronology protection. Machines that work only because they obey unseen rules. Why chemical rockets are already obsolete for interstellar dreams. When we look up at the stars and imagine traveling among them, it is tempting to think that the rockets we already use could one day get us there. After all, they carried us to the moon. They sent probes to every planet in our solar system, and they launched spacecraft that have now crossed into interstellar space. Yet when we measure those achievements against the distances between stars, the truth becomes stark. Chemical rockets, the technology we rely on today, are already obsolete for interstellar travel. They are powerful enough to lift us out of Earth's gravity, but on the scale of the cosmos, they are like rowboats in an endless ocean. The basic problem comes from how chemical rockets work. They burn fuel, releasing hot gases that shoot out the back and push the craft forward. This method has carried us through the space age, but its limits are written in physics. The energy stored in chemical bonds is tiny compared to the energy required to reach the speeds needed for star travel. Even our most advanced chemical rockets only reach a few tens of kilometers per second. That sounds impressive, until you realize that light itself covers that distance in less than 1,000th of a second. Against the speed of light, chemical rockets are not just slow, they are nearly standing still. Take the closest star system, Alpha Centauri. It is just over 4 light-years away, which is a short hop by cosmic standards. But even at the speeds of our fastest chemical-fueled craft, such a journey would take tens of thousands of years. That is longer than the span of all recorded human history. No society could realistically wait that long for a crewed mission to arrive, let alone return. The ships themselves would not last, the passengers would not survive, and the civilization that launched them would have changed beyond recognition by the time they reached their goal. This mismatch between our rockets and the distances involved explains why interstellar travel has remained more of a dream than a plan. We can build larger rockets, stack more fuel tanks, and design more efficient engines. But chemical energy itself is the bottleneck. There is simply not enough stored power in chemical reactions to push a craft to even a fraction of light speed. The faster you try to go, the more fuel you need to carry. But the more fuel you carry, the heavier the ship becomes, which demands even more fuel. It is a trap built into the very math of propulsion, a trap chemical rockets can never escape. We see this clearly in the history of our own missions. The Apollo rockets, towering machines filled with explosive fuel, managed to send astronauts to the Moon, a distance of only about 400,000 kilometers. The Voyager probes, launched in the late 1970s, took advantage of gravitational assists from giant planets to reach the edge of the solar system. Even with that help, Voyager 1 is moving at around 17 kilometers per second relative to the Sun. At that pace, it will need more than 70,000 years to reach the next star. These numbers are sobering reminders of how limited our progress is when measured against the galaxy. Chemical propulsion works for Earth orbit, it works for moon landings, and it works for robotic exploration of nearby planets. But it does not scale up to the stars. The gulf is simply too vast. For humanity to have any chance of becoming an interstellar species, we must leap beyond rockets that rely on burning fuel. We must search for engines that do not crawl along at kilometers per second, but approach fractions of light speed, or more. That is why ideas like nuclear propulsion, antimatter engines, and even faster-than-light concepts keep returning to the conversation. They are born from necessity. If the universe's distances were smaller, chemical rockets might be enough. We could imagine slow but steady voyages, generation ships drifting between stars, carrying human life across centuries. But the cosmos does not bend to our comfort. Stars are scattered across millions of light years. Galaxies stretch farther than our eyes can see, and even our nearest neighbors demand impossible journeys with current technology. The dream of faster-than-light travel arises because every other tool we have feels like trying to cross an ocean with a paddle. To accelerate a ship to a significant fraction of light speed with chemical fuel, you would need tanks larger than planets, stacked one after another in a chain of absurd proportions. The energy demands outstrip anything our engines can supply. Even with perfect efficiency, there is not enough chemical energy in all the reserves of Earth to make such a mission practical. The universe does not care how much we hope or plan. The physics of fuel and mass dictate the hard limits. This reality has forced scientists and engineers to think differently. If we cannot push ourselves to the stars with chemical fire, perhaps we must find ways to bend the problem. Concepts like light sails use the push of photons rather than propellant. Nuclear fusion and antimatter promise far more energy per unit mass than chemical bonds. And beyond those, ideas like warp drives and wormholes try to sidestep propulsion entirely by reshaping spacetime. Each of these approaches comes with challenges that may take centuries or longer to solve, but they all start from the same recognition. Chemical rockets cannot do the job. Our dependence on rockets today is not a failure, it is a stage. Rockets got us into space at all, something that once seemed impossible. They opened the path to exploration and discovery. But as soon as we think beyond the planets, their limits become clear. They are tools for local travel, not cosmic journeys. To keep dreaming of the stars, we must accept that the age of rockets is already behind us, even as we continue to use them for near-Earth missions. This shift in thinking mirrors the way past explorers faced the limits of their own technology. Wooden ships could cross oceans but not survive the storms of polar seas. Steam engines carried trains across continents but could not reach the skies. Every era of exploration eventually meets the boundaries of its tools, and those boundaries force a leap into something new. For space travel, that leap is away from chemical fire and towards something far more radical. Fusion, antimatter and beyond, still too slow for the stars. When people look beyond chemical rockets and imagine what might replace them, Fusion and antimatter often come up as the most exciting candidates. Both promise far more energy than the fuels we use today. A fusion rocket, in theory, would harness the same reaction that powers the sun. It would bring together light atoms, like hydrogen isotopes, and fuse them into heavier ones, releasing enormous amounts of energy in the process. Antimatter rockets would go even further. When antimatter touches normal matter, the two annihilate each other, converting their entire mass into pure energy. Compared to the tiny fraction of mass that chemical reactions turn into motion, these ideas sound like miracles waiting to happen. They could, on paper, carry ships at fractions of the speed of light. But here is the problem. Even if they worked as imagined, they would still be too slow when the stars themselves are tens of trillions of miles away. Fusion propulsion is not simply a dream. Many scientists have tried to map out how it might look in practice. The most famous example is the concept known as Project Daedalus, designed in the 1970s by the British Interplanetary Society. The design pictured a spacecraft several kilometers long, powered by pellets of deuterium and helium-3 that would be ignited by electron beams. It would have no crew, only instruments, because even under its boldest predictions, the trip to another star would take half a century. That was considered fast compared to everything else. Still, Daedalus was meant only as a one-way robotic probe, not something that humans could realistically use for exploration. And that was under the most optimistic circumstances. Building such an engine would require technology we do not yet have, especially for handling helium-3 in the quantities imagined, as it is rare even on Earth. Later projects tried to refine the idea. Project Icarus, a successor to Daedalus, asked whether updated technology could make fusion rockets more realistic. It did not dismiss the idea, but it did show that scaling up to the level required is beyond anything humanity has built so far. A fusion power plant on Earth is already a major engineering challenge, and even the largest experiments like ITR in France are not close to producing continuous net energy. To shrink that down, or scale it up, to a rocket engine that can run for decades in space is an even greater challenge. Even if it worked, fusion engines would likely reach only 10% of the speed of light, maybe a little more. That sounds quick, but to get to Alpha Centauri, the closest star system, would still take about 40 years at that speed, and slowing down at the other end would require just as much fuel and time. Antimatter engines on paper look far more promising. Because matter and antimatter annihilate completely, they release more energy per unit of mass than any other reaction we know. Just a few grams could match the energy output of entire rockets full of fuel. Designs have imagined magnetic nozzles that would direct the products of these annihilations into a thrusting beam. If this worked, speeds up to half the speed of light might be achievable. But the stumbling block is the antimatter itself. Producing it is incredibly inefficient. Particle accelerators like those at CERN can create antimatter particles, but at rates so small that it would take billions of years to make even a kilogram. Storing it is another challenge. Antimatter cannot touch the walls of any container, or it will annihilate instantly, so it would have to be held in magnetic traps, which are fragile and energy-intensive. A spacecraft carrying tons of antimatter would be less like a rocket and more like a floating bomb. Even if we solved these issues, time remains the enemy. Half the speed of light sounds amazing, but it would still take 8 years to reach Alpha Centauri, and that is without slowing down. To cross the galaxy at such a speed would take hundreds of thousands of years. For a civilization, those are impossible timescales. No culture could sustain a project across so many generations without it breaking down. The crew, if there were one, would live and die many times before arrival. Suspended animation or generation ships are often brought up as answers, but both come with their own problems. Keeping people alive for centuries in a closed environment may be as difficult as building the engine itself. Some researchers suggest that antimatter could be mixed with fusion to create a hybrid system. The antimatter would ignite fusion reactions, reducing the need for massive energy input, and in turn, the fusion would provide thrust. This makes the system more efficient, but does not solve the fundamental speed problem. The distances between stars are simply too vast for any sublight system to make them feel within reach. Even at 10% the speed of light, a ship would take centuries to cross to many of the nearest stars. And when we imagine exploring the entire galaxy, the numbers stretch into millions of years. This is the sobering truth. Even the boldest concepts we can design are still shackled by time. They turn interstellar travel into something possible, but not practical. They show that leaving the solar system can be imagined, but they do not make it something a civilization could rely on for expansion. In many ways, they are stepping stones. They might let us send robotic probes or perhaps a few brave crews to nearby stars, but they do not provide a path to true exploration of the cosmos. If a species wants to move beyond its home system and make the galaxy its home, then moving faster than light may be the only way. Sublight engines, no matter how advanced, will always be bound to the slow crawl of physics as we know it. Fusion and antimatter give us glimpses of what might be possible, but they also remind us of the limits. They promise great leaps forward, but not enough to cross the cosmic ocean in a way that feels alive to the beings making the journey. They make us dream, but they also show us why dreaming of faster-than-light travel is something that will not go away. Cosmic distances that make a mockery of relativity's limits. The Milky Way galaxy, our home, is about 100,000 light-years across. That number is almost too large to mean anything. A light-year is the distance light travels in a single year, moving at nearly 300,000 kilometers per second. Even at that unbelievable speed, it takes 100,000 years to cross from one side of the galaxy to the other. To put it another way, if humanity had launched a ship the day our species first appeared on Earth, it would still be only a tiny fraction of the way across the galaxy today. And that is just our galaxy. The nearest large galaxy to us, Andromeda, is more than 2 million light-years away. Light that left it before humans even existed is only now reaching our telescopes. And Andromeda is not unusual. It is just the nearest neighbor in a universe filled with galaxies. Many lie tens, hundreds, or even billions of light-years away. The scale is so great that traveling to another galaxy, even in imagination, feels like trying to swim across an ocean that has no shore. When Albert Einstein's theories set the speed of light as the ultimate limit, the universe suddenly looked like a cage. The enormous distances we now measure are not just inconvenient, they are final. They mean that even if we built ships that could travel at a fraction of light speed, journeys across the galaxy would take hundreds of thousands of years. Journeys beyond it would take millions. For all practical purposes, we are locked in a bubble that extends only a few light years in any direction, where perhaps a handful of nearby stars could be reached by extraordinary effort. Consider Proxima Centauri, the closest star beyond the Sun. It is about 4 light-years away, which does not sound so bad when compared to the 100,000 light-years of the Milky Way. Yet even that short hop is enormous on human scales. The fastest spacecraft humanity has ever built, the Parker Solar Probe, travels at around 700,000 kilometers per hour. At that speed, reaching Proxima Centauri would still take more than 6,000 years. That is longer than the entire history of civilization. So even the nearest star is unreachable with anything close to our current abilities. Multiply that distance by thousands and you begin to see how the universe remains untouchable to us. The Milky Way itself is so vast that we barely know our own neighborhood. Our solar system orbits the center of the galaxy, but it takes about 230 million years to complete a single orbit. The last time our solar system was in this position, the dinosaurs were roaming Earth. That is the timescale of our galaxy's motion, and it shows how large the stage truly is. Stars we see in the night sky are close by in galactic terms, mere tens or hundreds of light years away. Yet even those would take dozens of lifetimes to reach with sublight ships. The truth is that relativity does not just slow us down, it makes most of the galaxy permanently off limits. When astronomers point their telescopes outward, they find galaxies stacked one after another, receding into the darkness. The observable universe itself is about 93 billion light-years across. That number is so large that it stops being imaginable. Even light, the fastest thing there is, would take longer than the age of the universe to cross it. This creates a strange feeling. The universe is filled with wonders, but most of them are forever beyond us. The laws of physics make sure of it. If nothing can outrun light, then nothing we build will ever carry us beyond our own small patch of space. Say a ship could somehow travel at 10% of the speed of light. That would be astonishing compared to anything we have today. It could reach Proxima Centauri within a human lifetime, but that same ship would take 1,000 years to cross to a star just 100 light-years away and 1 million years to get across the Milky Way. Even with technology that bends imagination, the math never works in our favor. Time always stretches out, mocking our desire to explore. This reality forces us to think carefully about what exploration means. Perhaps we can visit our own solar system, building colonies on Mars, Europa, or Titan. Perhaps we can send robotic probes to a few nearby stars, waiting centuries for their signals to return. But the grand vision of a civilization spreading across the galaxy runs into the brick wall of cosmic distance. Without faster-than-light travel, the dream collapses into missions that take longer than civilizations last. It is almost as though the size of the universe was set up to be unreachable. On Earth, exploration worked because there was always another shore. Even the longest voyages could be completed in a few years. But in space, the shores are too far apart. You cannot carry enough supplies. You cannot keep people alive, and you cannot wait long enough for a journey that spans millennia. The size of the cosmos turns relativity into a kind of prison guard, standing at the boundary and reminding us that without breaking the speed of light, we will never leave our cell. There is also the unsettling truth that the universe is expanding. That means some galaxies we can see today with telescopes are already unreachable, no matter what. By the time we could dream of going there, they will have slipped over the cosmic horizon forever. In that sense, the distances are not just great, they are growing, pulling everything further away with each passing moment. Without faster-than-light travel, we are confined to one star system, maybe a handful more. With it, the galaxy and beyond open up. Relativity's limits make sense on paper, but when matched against the scale of the cosmos, they feel like a cruel joke. We can see the stars, we can measure their distances, but we cannot hope to reach them in any meaningful way. Why FTL is the only ticket to a galactic civilization. To dream of a galactic civilization is to dream of living among all the stars, not bound to one world or one system, but connected across this entire starry expanse. Yet when we look at the timescales of travel with our current technology, or even with the most ambitious propulsion methods we can imagine, the dream collapses. Human societies change drastically in just a few centuries. Empires rise and fall in mere centuries, sometimes even in decades. Languages evolve, cultures shift, and technology transforms the way we live. If it takes 1,000 years to send people to another star, then by the time they arrive, the civilization that sent them may no longer exist in its original form. Communication would be impossible, since even messages traveling at the speed of light would arrive centuries too late to matter. Colonization without faster-than-light travel becomes not a shared civilization, but a scattering of isolated outposts, each evolving on its own. The dream of a united galactic civilization collapses into islands separated by gulfs of space and time. Faster-than-light travel changes this picture completely. Suddenly, distances that once demanded millennia could be crossed in years or even days. The stars would no longer be remote, unreachable points of light, but accessible neighbors. Entire networks of planets could be connected, not just through physical presence, but through communication and trade. Cultures could expand outward without losing the bonds that tie them together. A galactic civilization is only possible if those ties can be maintained across the vastness, and only faster than light travel can make that possible. Even within a single galaxy, the numbers are staggering. If humanity were able to settle just one star system every 100 years using sublight travel, it would take millions of years to spread widely. A species could grow old and fade away before filling even a fraction of the galaxy. With faster than light travel, the timescales collapse. Expansion could become exponential, each colony spawning new colonies, all linked together in a living network. Instead of drifting apart into silence, humanity could thrive as one civilization across thousands of worlds. Civilizations that remain confined to one planet or one star system are fragile. A single catastrophe, whether natural or self-inflicted, can end them. Earth has faced mass extinctions before, and it will again, whether through asteroid impacts, supervolcanoes, or changes in the sun itself. Even if we master our home system, dangers remain, from cosmic radiation to the slow but certain evolution of stars into red giants. To endure across cosmic timescales, humanity must spread. To spread far enough, fast enough, requires breaking the light barrier. Faster than light travel is not just a dream of expansion, it may be a necessity for survival. Even the search for extraterrestrial civilizations is shaped by this reality. If intelligent life is common in the galaxy, why have we not seen evidence of it? One answer could be that without faster than light travel, civilizations remain trapped within their own small corners, unable to expand in ways we would notice. They might exist, but they are bound, just as we are. If faster than light travel is possible, then it changes the odds. Whether or not others have solved the problem may also hint at whether it can be solved at all. Throughout history, when frontiers have opened, humanity has expanded into them. Oceans were crossed, continents were settled, skies were flown, and orbits were conquered. Each new frontier reshaped us, giving rise to new cultures, new ways of thinking, and new possibilities. The galaxy represents the greatest frontier of all. But unlike the seas or the skies, it does not yield to gradual effort. It presents a wall that only faster than light travel can break. Without it, the frontier remains closed, no matter how much we push against it. If we remain bound to a small region of the cosmos, then in cosmic terms, we will be temporary. Stars die, galaxies change, and even universes evolve. To become lasting, to carve a permanent place in the cosmos, requires movement on scales that dwarf what light speed limits allow. A galactic civilization, connected and enduring, may be the only way for humanity or any intelligent species to truly leave a mark. That mark cannot be made slowly. It demands a leap beyond the barriers of physics as we know them. Becoming a Type 3 civilization demands breaking the limit. The Kardashev scale was designed as a way to think about the possible levels of growth for civilizations. It begins small, with a Type 1 civilization harnessing all the energy of its planet, then moves to Type 2, capturing the full output of its star. Type 3 is the Great Leap, the moment when a civilization takes control of energy on the scale of an entire galaxy. It is not a small step up, but a jump of such magnitude that it almost seems impossible. Yet if we want to think about humanity's farthest potential, it becomes the natural horizon. The problem is that without faster than light travel, this goal may remain forever out of reach. The very definition of a Type 3 civilization assumes not only massive power, but massive reach, and time becomes the main enemy. The Kardashev scale may not state it outright, but hidden in the Type 3 definition is an assumption. To even dream of such reach, you must find a way to break the speed limit set by relativity. The challenge is not just travel, but coordination. To command an entire galaxy, a civilization would need to communicate across vast distances. At light speed, a message from one side of the Milky Way to the other would take 100,000 years to arrive. That is longer than human civilization has existed on Earth. Without FTL communication, there would be no shared identity, no common governance, and no way to act as a single entity. Type 3 requires unity, and unity, at galactic scales, demands communication that beats the clock. This raises the possibility that Type 3 civilizations may not exist at all if FTL is impossible. Perhaps this is one reason the universe looks silent to us. If all intelligent species are trapped by the same barrier, then none of them can ever spread wide enough to leave obvious footprints. They may burn bright around their home stars, even build megastructures, but they cannot leap far enough to dominate a galaxy. Their signals fade before crossing interstellar distances, and their works remain confined to small pockets of space. But what if a civilization did find a way? It could build Dyson spheres around stars, harnessing nearly all their light. It could link these systems into networks that beam power across space. It could turn dead worlds into machines, black holes into engines, and nebulae into raw material for vast projects. In such a galaxy, stars would no longer burn unclaimed. They would be harvested, guided, and used. The galaxy itself would glow with artificial light, its natural beauty overtaken by deliberate order. Such an outcome is the logical end of intelligence, unconstrained by speed. But again, the dream hinges on FTL. Stars live for billions of years, but even that may not be enough. At sublight speeds, traveling from one end of the galaxy to the other could take longer than many stars remain stable. By the time a civilization reached them, those stars may have burned out or transformed into something else entirely. The galaxy is not frozen in place, waiting to be harvested. It evolves, shifts, and decays. If you cannot move quickly enough, you will always be chasing what is already gone. FTL becomes not just a convenience, but a survival tool. It would allow a civilization to act while the resources are still usable. Without it, the best opportunities vanish before they can be reached. Some propose that a civilization could send out self-replicating machines, slow probes that build copies of themselves as they travel from star to star. Over millions of years, such a fleet could, in theory, spread throughout the galaxy. But while that is an interesting thought, it falls short of the Kardashev dream. Machines drifting through the dark, working alone and taking ages to report back, do not make a civilization. They make an echo. They make a trace of expansion, but not the living, vibrant command of galactic energy. A Type 3 society, by its very definition, must be active, coordinated, and present. That presence demands speed that machines alone cannot supply. The heart of the matter is that the universe is too large for patience. To reach Type 3, something must break. Maybe it would be through shortcuts like wormholes, bending space itself to skip across distances. Maybe it would involve exotic particles or fields that allow information and matter to slip around the edges of what we know. Or maybe it is something no one has imagined yet, something that rewrites not only physics, but our entire understanding of reality. If we accept that FTL is impossible, then we also accept that our growth has a ceiling. We may reach Type 2, mastering our sun and turning it into a near-infinite power source, but beyond that, we are caged by distance. If, however, FTL is possible, then the ceiling lifts. The galaxy opens. Billions of stars wait to be touched, billions of worlds to be reshaped, billions of years of energy to be claimed. Would breaking light speed allow us to escape a dying universe? Stars are not eternal. They burn their fuel, shine for billions of years, and eventually fade. Galaxies which are made of those stars will grow darker as the ages pass. Over unthinkably long stretches of time, black holes will swallow matter, radiation will thin out, and the universe will move toward what is often called heat death. It is a state where everything is spread out too evenly, where there is no energy left to power life, stars, or even machines. If this is where the cosmos is headed, then any civilization that lasts long enough would have to face a terrible question. Can anything be done to escape this fate? Most ways of thinking about this problem seem to run into dead ends. Even the most advanced species we can imagine would eventually run out of resources in a dying universe. Energy would no longer be available to fuel great projects or to sustain life as we understand it. But there is one idea that stands apart from the rest: faster than light travel. If breaking the limit of light speed is possible, it could open the door to leaving not just a galaxy or a cluster of galaxies, but leaving the universe itself. If the universe we live in is doomed, then staying within it is not a long-term solution. But if there are other universes, other regions of reality beyond our own, then they might not share the same fate. Some could be young, filled with stars and energy. Some could be entirely different, with rules of physics. The challenge is reaching them, and light speed, as we know, sets a boundary. If we cannot cross it, then we may be locked inside with no escape. But if we can, then the situation changes. Imagine facing the end of stars. Civilizations that had survived billions of years would already have migrated between stars, stretching out their lifespans as much as possible. They could build megastructures to gather the last bits of energy, or feed black holes with matter to tap into their radiation. These efforts could prolong existence, but they would not change the final direction of time. Energy would still thin out. The temperature of space would still sink toward absolute zero. The lights would still go out. At that point, the only true solution would be to leave. Would breaking light speed make this possible? Perhaps. One idea is that if universes are like bubbles in a larger reality, then reaching the edge of ours and crossing into another might be achievable if we can move faster than light. At present, such an edge is infinitely far away. Space keeps expanding, so even if you traveled at light speed, the edge would keep moving away from you. But FTL changes the rules. Instead of being bound to the speed of expansion, a ship or civilization could jump across the fabric of space-time itself. Some scientists have speculated that black holes might connect to other regions of space and time. Wormholes, if they exist, could serve as tunnels to other universes. If such shortcuts are possible, then the death of our universe need not be the end of life. Civilizations might build their final hope around creating or stabilizing such pathways, stepping into a new universe before their own collapses into silence. But there are difficulties too. Even if FTL travel is possible, it may not be safe. Imagine entering another universe where the rules of physics are hostile. The forces might be so strong or so weak that matter as we know it cannot hold together. Stars might not form, or they might explode too quickly. There might be no stable atoms at all. In that case, escaping would only lead to destruction. A civilization would not know in advance what awaits on the other side. They could only gamble, sending scouts or probes into the unknown. Another concern is whether any civilization could even survive long enough to face these choices. The timescales we are talking about are vast beyond imagination, trillions upon trillions of years. By then, even the memory of Earth, the Milky Way, and our current universe would be ancient history. If some intelligence still remained, it would likely be so changed, so far beyond us, that it may not even resemble life anymore. Perhaps it would exist as patterns of information, stored and maintained by machines or quantum processes. For such beings, survival might not mean the same thing it does to us, but the drive to continue could still push them toward FTL as the only escape route left. What if the idea of escaping into another universe has already been attempted? If civilizations before us reached this level, maybe some of them broke light speed and left. This could be another explanation as to why the universe appears silent to us now. Perhaps the long-lived civilizations do not stay here forever, they move on. If universes themselves are born and die, then entering another one may only start the clock over again. It could buy time, perhaps trillions of years, but eventually that universe too would face its end. In that sense, FTL may not provide a final solution, but rather a repeating cycle of escapes. Civilizations might move from one universe to the next, like travelers hopping from island to island, always staying ahead of the flood, but never reaching true safety. For a civilization with the means to attempt it, breaking light speed could be the ultimate survival strategy. It may not guarantee eternity, but it would open up options. It would change the story from one of doom to one of possibility. Instead of fading with the stars, life might find a way to keep moving, reshaping its destiny with every leap. Would faster-than-light travel collapse the Fermi paradox? The Fermi paradox starts from a simple question. If the universe is filled with stars, planets, and the ingredients for life, then where is everybody? With billions of potentially habitable worlds just in our own galaxy, the odds seem high that at least some of them should have produced intelligent beings long before us. Yet when we look into the sky, we see nothing. No signals, no megastructures, no fleets of ships spreading from star to star. It is a silence that feels too loud, a gap between what should be and what we actually observe. Faster-than-light travel adds a new edge to this puzzle, because if it is possible, then the paradox becomes even deeper. If FTL were achievable, then advanced civilizations would not be bound by the slow crawl of sublight journeys. Instead, they could leap between stars with ease. Distances that currently take thousands or millions of years to cross could be shortened to days, weeks, or even moments depending on the technology. Expansion would no longer be a project of eternity, but of centuries or less. A species that discovered FTL could, in theory, spread across the entire galaxy in a timescale far shorter than the age of the Milky Way. Since our galaxy is over 13 billion years old, there has been more than enough time for such civilizations to emerge, expand, and leave undeniable traces. Yet we see nothing. If FTL is real, that absence becomes harder to explain, not easier. One possibility is that FTL is possible, but extremely rare to achieve. Maybe it requires a level of intelligence or resources that only a handful of civilizations could ever reach, and perhaps those civilizations quickly vanish due to internal collapse or external dangers. In this scenario, the silence we observe could be the silence of civilizations burning too fast. They touch FTL, leap outward, and then falter before their presence spreads far. If this is true, then FTL doesn't collapse the paradox, but instead highlights a grim filter, a barrier that few, if any, can pass. Another angle is that FTL could be possible, but also dangerous. The laws of physics as we know them warn that faster-than-light motion might lead to paradoxes in time, where cause and effect break down. Perhaps civilizations that experiment with FTL trigger catastrophic events, either on themselves or on their surroundings. Imagine an unstable form of propulsion that rips apart the space it touches, destroying planets and stars in its path. If so, then FTL might exist, but every attempt to wield it ends in ruin. The quiet skies could be the aftermath of civilizations learning that lesson the hard way. But what if the opposite is true? What if FTL is not just possible, but relatively easy to achieve for advanced species? In that case, the paradox becomes even more haunting. If the galaxy could be crossed quickly, then it should already be full of travelers, colonizers, or at least explorers. Earth itself should have been visited long ago. We should see the marks of alien engineering on nearby stars or receive signals that travel faster than light. The fact that we do not may mean something stranger is happening. Some suggest that civilizations with FTL may deliberately avoid us, following a kind of prime directive where younger species are left untouched. Others suggest that we are inside a kind of preserve, isolated from the wider community until we are ready. There is also the possibility that we are simply too early. Perhaps FTL is possible, but no civilization has yet mastered it. In this view, we are not late to the party, but early, living in a galaxy that has not yet awakened. If that is the case, then the paradox may not be a paradox at all, but a timing issue. The silence would not mean emptiness, but anticipation. The first civilizations to master FTL would change the picture forever, and maybe humanity could be among them. Yet this explanation feels fragile, given how old the galaxy is. Billions of years have passed, and it seems unlikely that we would happen to exist in the one moment before the Great Expansion. Some thinkers argue that the absence of alien civilizations might be evidence that FTL is impossible. If it were achievable, we should see its consequences everywhere, but we do not. Therefore, the simplest conclusion is that the speed of light truly is the limit, and nothing can break it. The quiet sky is not a mystery to be solved, but an answer already given. FTL is forbidden, and no one has ever escaped it. That would explain the stillness and align with everything physics currently tells us. Yet for many, this answer feels unsatisfying, because it means the dream of a galactic civilization is forever closed. Another possibility is that FTL civilizations are out there, but we cannot recognize them. Their methods of travel and communication might be so far beyond our understanding that they leave no trace we can detect. Perhaps they do not use energy in visible ways or build structures we would recognize. Maybe they slip through dimensions we cannot measure or fold themselves into forms of existence that blend with the background. To us, the galaxy would appear empty, even though it is alive with activity. In this version, the paradox remains only because of our blindness, not because of their absence. The silence could also be a choice. If FTL is real, civilizations may decide that expansion is not worth the risk. Crossing the stars might invite conflict, spread instability, or attract dangerous attention. A galaxy filled with rival FTL empires could be a violent and unstable place. To avoid this, most civilizations may choose isolation, keeping their power hidden rather than projecting it outward. In that case, perhaps wisdom at higher levels means restraint. Would we become the first to spread outward, blazing a trail across the galaxy? Or would we simply discover why others have not done so? The Fermi paradox suggests that something blocks civilizations from filling the stars. If FTL is real, then that block must be cultural, technological, or existential. Either civilizations destroy themselves, decide not to expand or operate in ways we cannot perceive. Each answer carries implications for our own future, for what kind of species we might become if we hold the key to the stars. Dark forest theory, reimagined in a universe with FTL predators. Imagine standing alone in a dense forest at night. You cannot see far ahead. The trees muffle sound. Every step you take might betray your position to hidden watchers. This is how some thinkers describe our universe under the dark forest theory. The idea is that in a cosmos full of potential life, no one speaks, because speaking is dangerous. Broadcasting your presence might invite attack from others who, fearing you, choose to strike first. If you do not act, you might be destroyed. Silence becomes the only safety. In the traditional version, the forest is vast and travel between stars is slow. Even if an enemy detects you, it might take thousands of years for them to arrive. There is still a sense of distance, a barrier of time. But if faster-than-light travel exists, the forest changes entirely. Suddenly, the predators are not distant shadows creeping for millennia. They are hunters who can leap across the dark in an instant. The silence becomes even deeper because any sound might bring death not in centuries, but perhaps within days or hours. In this reimagined forest, the fear does not just lie in being found. It lies in the speed of response. If a hostile civilization can jump across light years as easily as stepping across a stream, then the cost of striking first becomes trivial. They do not need to wait or plan across generations. They can act immediately, wiping out a potential rival before it has any chance to grow. What might have once been a cold war of patience turns into a deadly game of reflexes, where hesitation means extinction. This kind of universe would be shaped by paranoia at a galactic scale. Any hint of a signal, any accidental broadcast, could be enough to spark an attack. Civilizations would learn to bury themselves deep, shielding their worlds, masking their energy use, camouflaging their signals to look like natural cosmic noise. They would not only be silent, they would be invisible. Yet invisibility is never perfect. Every planet leaks heat, every machine hums faintly. A predator with advanced sensors could still pick up these signs. And if they can reach you faster than you can react, survival becomes almost impossible. Without FTL, the decision to attack is weighed against the long journey. A hostile species might hesitate if the target is thousands of years away. By then, the target could advance, defend itself, or even retaliate. But with FTL, there is no hesitation. The scales tip heavily towards striking first. Why wait when you can ensure your own survival instantly by eliminating a potential threat? The galaxy could become a place where trust never forms, because trust is too dangerous. Imagine the psychology of such civilizations. Generations would grow up under the doctrine that silence is survival, teaching children never to reveal themselves, never to imagine peaceful contact, because the risk is too high. Perhaps entire cultures would revolve around secrecy and suspicion. Their myths might not celebrate exploration or curiosity, but instead warn of the unseen dangers lurking in the dark. Expansion would be cautious, every step forward wrapped in layers of concealment, and always the knowledge that a mistake could mean the sudden end of everything. Every civilization is forced into the role of predator, whether they wish it or not. In such a universe, striking first might not come from malice but from fear. The mere fact of detecting another advanced species might trigger an automatic choice. Destroy them before they destroy us. Even peaceful civilizations might find themselves becoming predators simply because the alternative is extinction. If such a pattern exists, then the galaxy might be full of wreckage. Civilizations rising, reaching for the stars, giving off the faintest signal, and then gone, erased before they could grow further. Whole worlds reduced to ruins, not because of open wars, but because of quick, silent exterminations. Perhaps in this model, the stars are littered with the graves of cultures that dared to speak too loudly. And we, still primitive, still new to the forest, have simply not yet drawn attention. FTL predators might not even need to wait for signals. They could roam the galaxy like hunters, scanning systematically, seeking out life before it becomes advanced. The moment a planet begins to industrialize, the predators could intervene, ensuring it never reaches a point of danger. To them, it might be routine, like pest control, a necessary duty to preserve their own survival. For the victims, it would be an invisible and unstoppable doom. Even the smallest technological slip, a radar ping, a stray transmission, a failed heat shield on a power station, could be catastrophic. Civilizations would not only fear being detected in the present, but they would also fear the traces left in the past. A careless transmission made centuries ago might already be on its way to revealing their location. With FTL hunters, that old mistake could bring destruction at any moment, without warning. This also means that the idea of diplomacy becomes nearly impossible. Without time delays, there is no gradual building of trust. A predator could appear suddenly, and by the time a signal of peace is sent, it might already be too late. In fact, peace offerings might themselves be seen as threats, evidence that the other side is advanced enough to reach out and thus advanced enough to pose danger later. In a universe like this, communication itself might be a weapon, a way to bait others into revealing themselves. The galaxy might not even need many predators to remain silent. Even if only one or two species chose this path, their reach could spread fear across thousands of systems. Civilizations would assume that silence is universal law because breaking it risks contact with those hunters. Silence becomes contagious, reinforced by the few examples of destruction. The vast majority would remain hidden, not because they were attacked directly, but because they feared being next. In this version of the Dark Forest, the silence of the universe is logical. It is survival. We do not hear anyone because no one dares to speak. The predators are not bound by distance or time. They can strike faster than light, without hesitation, without warning. And so the forest remains dark, deep, and cold. Could FTL show us whether the universe is finite or infinite? One of the oldest questions humans have asked is whether the universe goes on forever, or if it has an edge. When we look at the night sky, it feels endless. No matter how far we point our telescopes, there are always more galaxies, more stars, more light reaching us from deeper space. Yet our view is not limitless. There is a cosmic horizon, beyond which light has not had enough time to reach us. At present, we are trapped within this horizon. Our telescopes, no matter how powerful, cannot see past it. For now, we can only guess whether the universe is infinite or finite, using mathematics, theories, and indirect clues. But what if faster-than-light travel became possible? Suddenly, that question would no longer be unreachable. FTL would allow us to step outside the cage of the cosmic horizon. Instead of waiting billions of years for light to carry information, we could cross that gulf ourselves. Imagine a ship that could leap past the edge of the visible universe, reaching regions forever hidden to our eyes. We would not just be guessing anymore, we could go and see. If the universe is infinite, then we would expect the journey to continue without end. Galaxies would keep appearing, structures would repeat at larger scales, and the starscape would stretch on forever. If the universe is finite, however, then a traveler might eventually find a boundary, an edge, a change, or perhaps a loop that bends back on itself. The very thought of encountering an edge of the universe is difficult to imagine. What would it look like? Would space simply stop, a sheer wall where nothing exists beyond? Or would it wrap around, like the surface of a sphere, so that traveling far enough in one direction brings you back to where you started? Many cosmologists lean toward the second idea, a finite but unbounded universe, where space is curved but without a clear edge. To a traveler using FTL, this could mean that after an unimaginably long journey, they might begin to see familiar galaxies returning into view, not because they reversed course, but because space itself loops. But if the universe is infinite, FTL would reveal a different picture. Beyond our horizon, galaxies would look much like the ones we already see. Clusters, filaments, and voids forming an endless web. The journey would never end, no matter how far you went. Even with FTL, an infinite universe could never be fully crossed. There would always be more, always regions untouched and unseen. The very act of trying to measure infinity would prove its vastness, as every leap only reveals more ahead. Faster-than-light travel could also test whether the laws of physics we know hold true everywhere. Right now, all of our theories are based on what we can observe within our horizon. Beyond it, conditions might change. Perhaps other regions of space follow slightly different rules, with variations in the constants of nature. With FTL, explorers could cross into those regions and test directly whether physics is universal or local. That alone would be as groundbreaking as discovering whether the universe has an edge. For centuries, we have argued whether infinity exists in reality or only in mathematics. The ancients imagined a cosmos bounded by crystal spheres. Later thinkers dreamed of endless worlds stretching outward without limit. Today, the debate is still alive among cosmologists. Infinity is hard to prove because you can never measure all of it. But with FTL, we could at least move far enough to get hints. If every direction we travel reveals more of the same structure, without repetition or boundary, we might grow confident that infinity is real. If instead we discover that the universe folds back or ends, then the question is settled in another way. There is also the possibility of something stranger. What if, beyond the horizon, the universe is not just more of the same, but something radically different? Perhaps there are regions where matter is absent, great voids larger than anything we know, or areas where galaxies cluster into unfamiliar shapes. Maybe even domains where time and space are bent in ways our current theories cannot predict. In practice, such exploration would be unimaginably difficult. Even with FTL, the distances involved are staggering. To leave our visible universe, a traveler would need to cross billions of light years. Still, if FTL is assumed, then those leaps are precisely what becomes possible. A civilization with such ability could scatter across the cosmos, testing whether infinity truly stretches forever, or whether the universe contains a hidden structure beyond our view. If we imagine this future, we must also consider what it would do to human culture. The knowledge that the universe is infinite would reshape how we see ourselves. In an infinite cosmos, every possible configuration of matter might occur somewhere. There could be endless Earth-like planets, endless variations of life, even endless versions of ourselves scattered through the vastness. On the other hand, if the universe is finite, then our home becomes more precious. The total amount of matter and energy is limited. The cosmos has a true shape, a whole that can, in theory, be mapped. Humanity's place in it would feel more defined, less lost in endless repetition. For now, we remain inside our horizon, cut off from knowing. But if someday faster-than-light travel became real, one of the first great journeys would not be toward any particular star or galaxy, but toward the horizon itself. Beyond that horizon lies the answer to one of the oldest human questions. Does the universe go on forever, or does it end? FTL as a bridge between universes. Imagine a civilization that has mastered faster-than-light travel. At first, they use it to reach new stars, build colonies, and span their galaxy. But after a time, they run out of places to go. Their galaxy is mapped, their neighbors are known, and even the distant galaxies drifting away on the tide of expansion may become reachable. Yet curiosity does not stop. What lies beyond it all? If universes exist side by side, then the greatest frontier is not across space, but through it. A civilization could leave the rules of its own cosmos behind. If their universe was fading, they could step into a fresh one, full of energy and new stars. If their own physics limited them, they might find new physics elsewhere. They could discover regions where time moves differently, where gravity is stronger or weaker, or where the very building blocks of matter are not the same. Of course, there are dangers as well. Other universes may not be friendly. Some could be filled with radiation so intense that no matter could survive. Some could be empty voids where nothing ever formed. Some could have constants of nature tuned so differently that atoms cannot exist or stars cannot shine. That means FTL travel across universes would carry enormous risk. It would be a leap into the unknown with no guarantee of return. Yet that risk might not stop anyone. Human history, and the history of exploration we imagine for other species, is full of examples of venturing into the unknown despite danger. If the stakes are high enough, then the leap may feel worth it. In fact, some might argue that this is the ultimate destiny of intelligence, not to remain within one universe, but to spread into many. Perhaps when you move faster than light, you are not simply skipping across long distances. Perhaps you are slipping sideways into another layer of reality. Wormhole theories hint at this. Depending on how space-time curves, the other end of a wormhole might open in another universe. In that case, FTL would be inseparable from multiverse travel. Every jump could carry the possibility of ending up not just across the galaxy, but outside of it. If FTL connects universes, then advanced beings might not limit themselves to exploring their own cosmos. They might already be travelers between many. The signs of their passage would be invisible to us, since they would not leave traces inside our universe. They would move through it as easily as we might walk across a room, only to step out the door into another house entirely. From our point of view, they would vanish without a trace. Our universe might be only a temporary stop, a way station on a much larger journey. Imagine not just stepping into another universe where the laws of physics are different, but into one where history itself is different. A universe where Earth formed in a different way, where life took another path, or where human civilization never rose at all. FTL could become a way of exploring not only the cosmos, but alternate histories, different outcomes of the same beginning. For a civilization with such power, exploration would be about knowledge, about curiosity, about experiencing the full scope of what existence has to offer. They might catalogue universes like we catalogue species, mapping the endless diversity of realities. They might even seed new universes of their own, creating fresh canvases of space and time, then traveling between them as easily as we travel between continents. If FTL connects universes, then perhaps it is already happening in ways we cannot perceive. Perhaps reality itself is full of travelers we cannot detect, moving between worlds that overlap with ours without ever touching it. We may live in a multiverse alive with motion, while remaining blind to it, because our technology has not yet taken the step beyond light. The dream of faster-than-light travel is often described as a dream of freedom, of breaking limits. But if it can bridge universes, then it becomes a dream of infinite frontiers, where each universe is only the beginning. And beyond every horizon lies not just more stars, but whole new realities. In that vision, the true purpose of breaking light speed is not to master one universe, but to explore them all. What are your thoughts about this kind of possibility? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.